The greatest mystery of the ancient world is not that its civilizations disappeared, it is that so much of their knowledge seems to have disappeared with them. Across every continent, remarkable monuments still stand with astonishing precision, despite surviving earthquakes, wars, and thousands of years of erosion. Archaeologists have uncovered their age, mapped their layouts, and studied every visible detail, yet many of the most fundamental questions remain unanswered. How were stones weighing hundreds of tons moved with such control? Why do certain structures display an understanding of engineering that appears far beyond their era? The more evidence emerges, the harder these places become to explain. Perhaps the ruins themselves are not the mystery. Perhaps what truly vanished was the knowledge that made them possible. Ptolemais, on the Mediterranean coast of present-day Libya, was one of the largest cities of ancient Cyrenaica. Yet, beneath its streets lies a technological mystery that archaeologists still struggle to explain. A gigantic underground water complex whose full engineering logic remains unknown. The ruins of Ptolemais were first systematically documented by European explorers during the 19th century, while major archaeological investigations expanded throughout the 20th century under Libyan, British, and later Polish missions. What researchers uncovered was not merely another Greco-Roman city. They found evidence of an urban infrastructure system so sophisticated that parts of its operation remain uncertain even after decades of excavation. The greatest mystery of Ptolemais is hidden underground. Beneath the city lies an enormous network of vaulted reservoirs commonly known as the Great Cistern Complex. The structure contains at least 17 interconnected chambers arranged beneath a large area of the ancient city. Estimates suggest the system could store approximately 7,000 cubic meters of water. To put this into perspective, that is enough water to fill nearly 3 Olympic-sized swimming pools. For a city located in a relatively dry region of North Africa, such storage capacity was not simply convenient, it was essential for survival. What makes the complex mysterious is not its size, but its design. Archaeologists can map the chambers, measure the walls, and reconstruct portions of the structure, yet they still debate exactly how the entire system functioned. Water entered through aqueducts and local collection systems, but the precise method used to regulate flow between the chambers remains unclear. Some researchers believe the reservoirs acted as a massive hydraulic regulator, stabilizing water pressure throughout the city. Others argue that the chambers operated as a multi-stage filtration system, designed to remove sediment before water reached public fountains and households. The engineering challenge was enormous. Water moving through interconnected reservoirs must be carefully controlled. Too much pressure can damage structures. Too little pressure can interrupt supply. Modern water engineers solve these problems using mathematical models, pressure gauges, and computerized monitoring systems. The builders of Ptolemais possessed none of these tools, yet they created a system that functioned for centuries. The unanswered question is how they calculated it. No surviving manuals describe the design process. No engineering drawings have been discovered. The physical structure survives, but the knowledge behind it largely vanished. This situation resembles other famous technological mysteries from antiquity. Roman marine concrete continues to puzzle material scientists because of its remarkable durability in seawater. The builders of the Antikythera mechanism created an astronomical computer nearly 2,000 years ago, yet almost no written explanation survived. Ptolemais presents a similar puzzle in the field of hydraulic engineering. The cistern complex becomes even more impressive when viewed in its broader urban context. Ancient Ptolemais covered approximately 280 hectares, making it one of the largest cities in Cyrenaica. Supporting a population of many thousands required a constant water supply for drinking, bathing, industry, sanitation, and agriculture. The city relied on an aqueduct system, extending more than 8 kilometers from inland water sources. Maintaining a stable flow across such distances required precise control of gradients. Modern surveys show that Roman and Hellenistic aqueducts often maintained slopes measured in only a few meters per kilometer. An error of even a small percentage could cause stagnation, overflow, or structural failure. How ancient engineers achieved such accuracy remains a matter of debate. The Greeks and Romans possessed surveying instruments such as the chorobates and groma, but many researchers believe these tools alone cannot fully explain the extraordinary precision seen across major hydraulic systems. Similar questions surround the aqueducts of Rome, the Pont du Gard in France, and the tunnels of Samos in Greece. Ptolemais belongs to this same category of ancient engineering enigmas. Another mystery involves the city's relationship with earthquakes. On July 21 AD 365, one of the most powerful earthquakes in Mediterranean history struck near Crete. Modern geological studies estimate a magnitude exceeding 8.0. The event generated a massive tsunami that devastated coastal settlements across the eastern Mediterranean. Cities such as Alexandria suffered severe destruction. Yet Ptolemais survived and continued functioning as an important regional center. Archaeologists still debate why. Was the city's infrastructure unusually resilient? Did its builders incorporate structural techniques that improved resistance to seismic activity? Were certain foundations specifically adapted to local geological conditions? Excavations reveal multiple phases of reconstruction, but the full explanation remains uncertain. Like many ancient technologies, the practical knowledge may have disappeared while the structures themselves endured. The harbour of Ptolemais presents another unresolved problem. Today, portions of the ancient port lie beneath the Mediterranean Sea. Underwater surveys have identified submerged architectural remains, harbour installations, anchors, and evidence of maritime activity. The existence of these submerged features raises difficult questions. How much of the coastline has changed since antiquity? Did tectonic movements gradually lower parts of the city? Did sea level changes alter the shoreline? Or did the earthquake of AD 365 permanently reshape the harbour environment? Researchers continue using underwater archaeology, sonar mapping, and coastal geology to reconstruct the original harbour layout. However, no consensus has emerged. Understanding the harbour is crucial because maritime trade formed the economic foundation of the city. Without knowing how the port functioned, historians cannot fully explain Ptolemais' rise as a major Mediterranean centre. The city's urban planning introduces yet another technological puzzle. Ptolemais was organised according to a remarkably regular grid system. Streets intersected at carefully planned angles, creating standardised urban blocks. Such layouts are common in Hellenistic cities, influenced by the principles associated with Hippodamus of Miletus, often called the father of urban planning. Yet implementing these designs on a large scale required sophisticated surveying methods. Modern archaeologists can reconstruct city plans using satellite imagery, GPS measurements, drones, and digital mapping software. Ancient surveyors relied on ropes, sighting instruments, geometry, and accumulated experience. Despite these limitations, they achieved results that continue to impress modern engineers. The question is not whether they succeeded. The evidence proves they did. The mystery is exactly how they maintained such consistency across hundreds of hectares without modern technology. Perhaps the most fascinating aspect of Ptolemais is what it reveals about lost knowledge. The city demonstrates mastery of water management, hydraulic engineering, surveying, architecture, logistics, and urban administration. These capabilities were not isolated achievements. They formed part of a complex technological tradition that developed over centuries. Yet much of that tradition vanished. Written records are incomplete, technical manuals are scarce, the engineers themselves are anonymous. What do you think was the greatest achievement of Ptolemaeus? The massive underground cistern complex, the long-distance water system, or the engineering knowledge that vanished with the city? Share your thoughts in the comments below. Discovered near Seville in southern Spain, only a few kilometers from the lower Guadalquivir River, the treasure of El Carambolo consists of 21 gold artifacts weighing roughly 2.7 kilograms. While it may initially appear to be just another ancient hoard among the many found across Europe and the Mediterranean, the collection has puzzled researchers since its discovery. For more than 60 years, archaeologists, metallurgists, and historians have sought to understand how craftsmen living nearly 2,800 years ago were able to create gold objects with such remarkable purity, precision, and consistency. As scientific analysis has advanced, the treasure has continued to challenge conventional assumptions about ancient metallurgy, trade networks, and the level of technological sophistication achieved during the early Iron Age. The discovery itself was surprisingly ordinary. In September 1958, workers preparing a site for a shooting club at El Carambolo accidentally uncovered a collection of gold objects buried beneath the ground. What initially seemed to be a cache of jewellery soon became one of the most important archaeological discoveries ever made in Spain. The treasure included massive necklaces, breast ornaments, bracelets, and decorative plates fashioned from solid gold. Archaeologists quickly realized that these objects were unlike typical Iberian artifacts. Their craftsmanship suggested connections to the wealthy and mysterious culture known as Tartessos, a civilization described by ancient Greek writers but still poorly understood today. The greatest mystery emerged when scientists began studying the metal itself. Modern analyses reveal that many pieces were manufactured from extraordinarily pure gold. In several objects, purity levels exceeded 90%, with only small amounts of silver and trace impurities remaining. To modern observers, this may not sound remarkable. Contemporary refineries routinely produce gold with purities exceeding 99.99%. But the situation becomes far more impressive when viewed through the lens of ancient technology. During the 8th and 7th centuries BC, there were no industrial furnaces, no chemical refining plants, no modern crucibles, and no scientific understanding of metallurgy. Yet somehow the creators of El Carambolo acquired and worked gold whose quality rivals some of the finest precious metal objects known from the ancient Mediterranean. This raises a question that remains surprisingly difficult to answer. How was such gold obtained? Natural placer gold can occasionally reach high purity, especially after long geological processes remove impurities. However, the consistency observed across multiple objects suggests something more sophisticated than simply collecting unusually pure nuggets. Some researchers have proposed that ancient craftsmen employed refining techniques capable of separating silver from gold more effectively than previously believed. Others argue that the raw material may have originated from exceptionally rich deposits within southwestern Iberia. Neither explanation fully resolves the puzzle. Experimental archaeology has demonstrated that achieving similar purity using reconstructed Iron Age methods is possible, but doing so consistently across kilograms of material requires enormous skill, knowledge, and labor. The treasure suggests that ancient metallurgists possessed practical expertise that modern researchers may still underestimate. The mystery deepens when compared with other famous gold treasures of antiquity. The gold mask of Tutankhamun, created around 1323 BC, contains gold of varying purity levels carefully selected for visual effect. Mycenaean gold objects from Greece often display significant differences in composition, even within the same artifact. Many Celtic treasures of later centuries reveal greater impurity levels than those observed at El Carambolo. Despite being separated by geography and culture, these comparisons reveal an uncomfortable fact. The craftsmen responsible for El Carambolo were operating at a metallurgical level comparable to some of the most sophisticated gold-working traditions of the ancient world. Purity alone, however, is only the beginning. The objects demonstrate astonishing manufacturing precision. Many ornaments were constructed from thin sheets of hammered gold shaped into complex geometric forms. The thickness of these sheets remains remarkably uniform across large surfaces. Producing such consistency is challenging even with modern hand tools. Gold is highly malleable, but it also deforms easily. Excessive hammering can create weak points, distortions, and microscopic fractures. Ancient artisans somehow controlled these variables with extraordinary effectiveness. Detailed examinations reveal carefully planned shaping sequences and evidence of repeated annealing, a process in which metal is heated and cooled to restore its workability. Such procedures require precise temperature control despite the absence of thermometers or modern furnaces. Some breastplates and decorative elements display a degree of symmetry that continues to fascinate researchers. Opposing curves mirror one another with remarkable accuracy. Edges align with minimal deviation. Decorative patterns maintain consistent spacing across entire surfaces. Today, such precision might be achieved through rulers, templates, calipers, and standardized measurements. No such instruments have been found associated with the treasure. This does not mean they never existed, but it raises important questions about how artisans organized production. Were geometric principles transmitted through apprenticeship systems? Did craftsmen rely on specialized templates made from organic materials that have not survived? Or did they possess practical mathematical techniques that left little archaeological evidence? The origin of the gold itself presents another unresolved puzzle. Southwestern Iberia was one of the richest metallurgical regions of the ancient world. The Rio Tinto mining district contains vast deposits of copper, silver, and precious metals exploited for thousands of years. Yet isotopic and compositional studies have not conclusively identified a single source for the treasure's gold. Some analyses suggest local origins. Others indicate possible connections to broader Mediterranean trade networks. During the period when El Carambolo was created, Phoenician merchants were establishing colonies along the Iberian coast. Their ships connected the western Mediterranean with regions stretching from present-day Lebanon to North Africa and beyond. If gold, techniques, or artisans move through these networks, the treasure may represent a fusion of technological traditions rather than the achievement of a single culture. This possibility lies at the center of one of archaeology's longest-running debates. Was the treasure created by the indigenous Tartessian civilization, by Phoenician craftsmen, or through collaboration between both groups? The answer matters because it affects how historians interpret the development of technology in ancient Iberia. If Tartessian artisans produced the treasure independently, then local metallurgical capabilities were far more advanced than traditionally believed. If Phoenician specialists created it, the treasure becomes evidence of technological transfer from the Eastern Mediterranean. The problem is that the artifacts contain features supporting both interpretations. Their forms resemble Near Eastern ceremonial objects, yet they were discovered in a region strongly associated with Tartessos. Decades of study have failed to produce a consensus. Recent excavations at El Carambolo suggest the site was a major sanctuary rather than just a settlement. This changed interpretations of the treasure, indicating it may have been sacred ceremonial equipment instead of personal jewelry. Several pieces seem too large and impractical for everyday use, likely designed to create a powerful visual effect. In ritual ceremonies, the highly polished gold surfaces would have reflected bright sunlight, making the wearer appear almost supernatural. The treasure's survival is equally remarkable. Gold is durable, but valuable objects are rarely left untouched for centuries. Someone deliberately buried these artifacts, and no one returned to recover them. Why? Some researchers propose that they were hidden during political upheaval. Others suggest they were deposited as offerings to deities. A third possibility is that they formed part of a ritual closure event associated with the sanctuary itself. No explanation fully accounts for all available evidence. The circumstances surrounding their burial remain almost as mysterious as their manufacture. What do you think is the most likely explanation? Did the artisans of Tartessos possess a lost metallurgical technology of their own, or was the treasure of El Carambolo the result of knowledge brought by Phoenician master craftsmen? Share your thoughts in the comments below. Buried beneath a low hill near modern-day Stuttgart in southern Germany, the Hochdorf chieftain's grave dates back roughly 2,500 years and contains evidence of wealth, engineering and scientific knowledge that seems surprisingly advanced for Iron Age Europe. Long before Rome dominated the continent, before paved roads connected distant regions, and before written records described the societies north of the Alps, an elite individual was laid to rest on a bronze couch, surrounded by gold ornaments, imported luxury goods, and enough equipment to host a feast for hundreds of people. Archaeologists expected to uncover the burial of a wealthy leader. Instead, they found evidence of a society far more sophisticated and interconnected than previously imagined. The story began in 1978 when archaeologists investigating a large burial mound at Hochdorf, near the Neckar River Valley, uncovered an extraordinary chamber preserved beneath layers of earth. Dendrochronological analysis of the oak timbers dated the burial to approximately 530 BC. Inside lay the remains of a man around 40 years old, standing nearly 1.87 meters tall, unusually large for his era. Around him were more than a dozen kilograms of bronze artifacts, imported Mediterranean goods, gold jewelry, drinking vessels, weapons, and one of the most remarkable pieces of prehistoric furniture ever discovered in Europe. Yet the deeper researchers examined the burial, the more difficult it became to explain how a society traditionally described as tribal had achieved such levels of technical precision. The burial chamber itself immediately raised questions. Measuring roughly 4.7 by 4.7 meters and enclosed within multiple layers of timber construction, the structure demonstrated a sophisticated understanding of load distribution and long-term preservation. Massive oak beams were carefully selected, cut and assembled into nested chambers designed to withstand centuries of pressure from the mound above. Modern engineers studying the structure noted that its builders successfully created a stable underground environment capable of preserving organic materials for more than 2 millennia. Such performance is remarkable when compared with many later medieval wooden structures that survived only a fraction of that time. The precision of the chamber suggests standardized planning, careful measurement, and a level of construction management rarely associated with Iron Age Europe. The famous bronze couch upon which the chieftain rested presents another puzzle. Nearly 2.75 meters long, it was supported by 8 bronze female figures cast with astonishing uniformity. metallurgical analysis revealed advanced bronze working techniques, including controlled casting temperatures and detailed finishing methods. Even more intriguing is the consistency among the decorative elements. The repeated motifs exhibit dimensional accuracy that implies the use of templates or standardized production systems. Yet no evidence survives for written engineering plans, mathematical manuals, or formal workshops comparable to those known from later classical civilizations. The object appears to belong to a manufacturing tradition whose underlying technical knowledge has largely vanished. Gold artifacts found in the grave deepen the mystery. The chieftain wore a magnificent gold neck ring, gold-decorated footwear, and numerous ornaments manufactured with exceptional precision. Microscopic examination has shown evidence of highly refined hammering and shaping techniques. Some decorative sheets were worked so thinly that producing them would have required careful control of metal purity and repeated cycles of heating and mechanical processing. Similar skills are seen in Mediterranean civilizations of the same period, yet the Hochdorf objects demonstrate that Celtic craftsmen possessed expertise equal to many of their southern counterparts. The existence of such craftsmanship forces archaeologists to reconsider long-standing assumptions regarding technological development north of the Alps. Trade connections represented in the grave are equally astonishing. Among the most important discoveries was a massive bronze cauldron capable of holding approximately 500 litres of liquid. Scientific studies indicate that it was probably manufactured in the Greek world, perhaps somewhere in the eastern Mediterranean. Transporting such an object across more than 1,000 kilometers without modern roads, wheeled freight systems, or organized imperial infrastructure would have required an extensive network of exchange. Similar imported luxury goods have been discovered at elite Celtic sites across Europe, suggesting that long-distance trade routes were far more sophisticated than once believed. Yet the mechanisms that maintained these networks remain poorly understood. No written records explain how goods, information and technology moved across such enormous distances. However, the greatest mystery of Hochdorf is neither its gold nor its imported treasures. It is the evidence for highly advanced brewing and beverage preservation technology hidden among the grave goods. Near the burial were 9 drinking horns, one of them nearly 5 litres in capacity. Residue analysis and associated archaeological evidence strongly suggest that large quantities of fermented beverages played a central role in the funerary rituals surrounding the chieftain. At first glance, this may seem ordinary. Ancient societies everywhere consumed alcoholic drinks. Yet when researchers examine the scale of production implied by the Hochdorf burial, a far more complex picture emerged. Brewing stable beer is not a simple process. It requires controlled germination of grain, careful drying of malt, precise management of fermentation conditions, and protection against contamination from bacteria and wild yeasts. Modern brewing science demonstrates that small variations in temperature, moisture, or storage conditions can ruin entire batches. Producing a drinkable product for a few households is one thing. Producing hundreds of litres for elite ceremonial consumption is something entirely different. Evidence from Hochdorf suggests exactly that level of production. The giant imported cauldron alone could hold approximately 500 litres. To fill even part of such a vessel would require enormous quantities of barley, water, labour, and technical knowledge. Experimental archaeology indicates that producing several hundred litres of beer could require hundreds of kilograms of grain and carefully coordinated processing stages. This implies agricultural organisation on a scale far beyond subsistence farming. More importantly, beer spoils quickly. Without modern refrigeration, maintaining quality becomes extremely difficult. Researchers believe Iron Age brewers may have developed sophisticated methods involving seasonal production, specialized storage vessels, controlled fermentation environments, and perhaps the use of natural preservatives. Some scholars have proposed that elite Celtic centres functioned as specialized production hubs, capable of creating beverages intended for large ceremonial gatherings. If true, these operations would represent an early form of industrial-scale food technology. Comparisons with other ancient societies make Hochdorf even more remarkable. In Mesopotamia, Egypt, and later Rome, brewing traditions were supported by urban administrations, written records, and specialized labor systems. At Hochdorf, no such documentation exists. Yet the archaeological evidence suggests comparable organizational complexity. The technology existed, but the manuals are gone. The expertise existed, but the workshops disappeared. What remains are indirect traces embedded within drinking equipment, residue chemistry, and the logistics required to sustain elite feasting. The burial mound itself provides further clues. Feasting appears to have been central to political power in Celtic society. Leaders may have reinforced alliances by hosting enormous gatherings where food and drink demonstrated wealth, authority, and access to distant trade networks. In this context, brewing was not merely food production, it was a strategic technology. The ability to produce, preserve, transport, and distribute large quantities of alcohol may have been as important to maintaining power as metallurgy or warfare. Was Hochdorf simply the grave of an extraordinary leader? Or is it evidence that an entire technological tradition flourished in prehistoric Europe and then disappeared almost without a trace? Few places in Roman Europe are as strange as the buried remains of Aventicum, the Roman city now known as Avenches, hidden beneath farmland and scattered medieval ruins in modern Switzerland. Archaeologists first began identifying the site systematically during the 18th and 19th centuries after massive stone walls, underground foundations, coins, mosaics, and fragments of Roman engineering repeatedly surfaced from the soil. What they eventually revealed was shocking. A city that may once have housed more than 20,000 inhabitants in a region considered too cold, too wet, and too unstable for large-scale Roman urban expansion. Yet Aventicum was not only built there, it thrived there, and many of its engineering methods still raise uncomfortable questions about how advanced Roman practical science may actually have been. Unlike Pompeii, which was frozen instantly by volcanic ash, Aventicum survived centuries of freezing winters, shifting groundwater, and alpine climate cycles. That alone should have destroyed most ancient masonry long ago. Modern concrete exposed to repeated freeze-thaw expansion often begins degrading within decades unless protected with advanced additives. Yet some Roman foundations in Aventicum remain structurally coherent after nearly 2,000 years. One of the biggest mysteries surrounding Aventicum is its water management system. Excavations uncovered underground channels, lead piping, stone-lined conduits, pressure-regulating reservoirs, and drainage systems extending beneath major districts of the city. Roman engineers are already famous for aqueducts, but Aventicum presents a far more difficult environment than southern Italy. Water pressure changes dramatically in alpine terrain, and freezing temperatures can rupture pipes with enormous force. Despite this, many channels were constructed with gradients so precise that modern surveys found deviations of only a few centimeters across long distances. That level of precision becomes difficult to explain when considering Roman surveying equipment. The Romans used tools such as the chorobates and groma for alignment, but maintaining hydraulic efficiency across kilometers without modern laser measurement would have required extraordinary calibration. Even small miscalculations would have caused sediment buildup, pressure instability, or destructive overflow. Some archaeologists believe Aventicum may have used primitive hydraulic balancing systems, similar in principle to modern surge regulation. Several buried basins appear positioned specifically to stabilize flow rates between elevation changes. If true, this would mean Roman engineers understood practical fluid dynamics far beyond what is traditionally attributed to the ancient world. The mystery deepens with the city's drainage infrastructure. Ground-penetrating radar surveys revealed networks of subterranean runoff tunnels designed to redirect excess groundwater away from public structures. Similar concepts are used in modern urban flood control systems. In some sectors, drainage layers beneath roads and buildings resemble contemporary geotechnical stabilization methods. This becomes even stranger when compared with many medieval European cities built more than 1,000 years later. Medieval settlements often suffered catastrophic sanitation failures, flooded streets and unstable foundations. Yet Aventicum appears to have implemented integrated drainage engineering centuries earlier. Another unresolved mystery involves the material composition of the city's mortar and foundations. Chemical analysis of surviving masonry revealed unusually durable lime-based mixtures containing crushed stone aggregates and mineral compounds that appear optimized for moisture resistance. Researchers comparing samples to Roman marine concrete from ports near Naples found surprising similarities in crystal formation. Modern studies of Roman concrete have shown that some ancient mixtures develop self-healing properties through the formation of calcium-aluminum silicate crystals when exposed to water. Microscopic cracks can partially reseal themselves over time. In modern infrastructure, self-healing concrete is considered cutting-edge experimental technology. Yet, traces of similar reactions appear inside Aventicum's foundations. What makes this difficult to explain is geography. Southern Roman concrete often relied on volcanic ash known as pozzolana, sourced primarily from regions near Vesuvius. Aventicum lies hundreds of kilometers away in Switzerland. Either massive quantities of specialized material were transported through Roman trade systems across mountainous terrain, or local engineers developed alternative formulations independently. Transport itself becomes another mystery. Aventicum's largest stones weigh several tons. Moving them through alpine regions without modern cranes or engines would have required coordinated logistics on a scale many historians underestimate. Roman transport calculations suggest that hauling stones of this size over wet terrain would have demanded hundreds of laborers, reinforced sled systems, and carefully engineered roadbeds. Those roads still survive. Roman roads around Aventicum continue to puzzle engineers because of their structural resilience. Beneath the visible paving stones, excavations revealed multiple compacted layers of rock, gravel, sand, and drainage material, arranged with remarkable sophistication. The deeper layers acted almost like shock absorbers, redistributing pressure and reducing water retention. Modern civil engineering uses similar multi-layer road foundations to combat frost heave, a destructive process in which freezing groundwater expands beneath roads and fractures the surface. In Switzerland's climate, frost heave can destroy asphalt highways within years if improperly engineered. Yet portions of Aventicum's roads remained stable for centuries. Some sections even contain side drainage channels buried beneath the roadway itself. These systems prevented water accumulation below the foundation, reducing freeze damage. It is an engineering strategy still used in modern, cold region infrastructure projects today. The city's amphitheatre presents another mystery: acoustics. Aventicum Amphitheatre was constructed with seating geometry that allows voices and sound waves to travel efficiently from the arena floor to upper seating rows without amplification. Acoustic tests conducted in surviving Roman theatres across Europe consistently demonstrate sophisticated sound behaviour. But Aventicum's design is particularly unusual because of the surrounding terrain and wind exposure. Researchers studying Roman acoustics discovered that curved stone surfaces and seating angles can naturally amplify frequencies associated with human speech. But achieving this effect consistently required empirical understanding of reflection, resonance, and spatial geometry centuries before formal acoustic science existed. Some historians argue Roman architects learned these principles gradually through experimentation. Others believe their understanding of sound propagation may have been far more mathematically advanced than surviving texts suggest. The city's heating systems also remain astonishing. Excavations uncovered hypocaust technology beneath villas and bathhouses, an underfloor heating network where hot air circulated through hollow chambers beneath stone floors and wall cavities. Similar systems would not become common in Europe again until many centuries later. What surprises modern engineers is the efficiency. Some reconstructed models indicate indoor temperatures may have remained relatively stable despite harsh winters outside. Certain homes even appear to incorporate double-wall insulation principles that reduced heat loss while limiting internal moisture buildup. That combination of thermal management, drainage engineering, and structural stabilization creates an uncomfortable comparison with later European history. In many ways, Aventicum appears technologically ahead of numerous medieval cities built long after Rome collapsed, and yet much of the city still remains underground. Radar imaging suggests large sectors of Aventicum have never been excavated. Buried foundations, unknown chambers, and unexplored infrastructure continue beneath modern fields surrounding Avenches. Archaeologists believe only a fraction of the ancient capital has been fully studied. Some subterranean anomalies detected beneath the city do not yet match known Roman layouts. There are indications of unusually deep foundations and possible industrial sectors hidden beneath later sediment layers. If future excavations confirm large-scale manufacturing zones, Aventicum may force historians to reconsider how industrialized some Roman provincial cities truly became. Casa Carana is a stone mystery standing in the eastern desert of Jordan. Built more than 1,300 years ago, it looks like a fortress, functions like a palace, and behaves like neither. Behind its thick walls lies one of the most puzzling engineering achievements of the early Islamic world, a building whose true purpose remains unknown and whose environmental design still surprises modern researchers. The structure stands approximately 60 kilometers east of Amman, along an ancient route connecting Syria, Arabia, and Mesopotamia. Constructed during the Umayyad period, around the early 8th century AD, Casa Carana belongs to a group of monuments commonly called the Desert Castles. Yet, unlike many of its counterparts, almost every aspect of this building raises questions. The site became known to Western scholars during surveys of Transjordan in the late 19th and early 20th centuries. Systematic archaeological investigations later revealed inscriptions dating to around AD 710, making it one of the earliest surviving examples of Umayyad architecture. What researchers expected to be a simple desert fortress quickly became one of the most confusing architectural puzzles in the region. The first mystery begins with the building's appearance. Viewed from a distance, Casa Carana resembles a military stronghold. Its square plan measures roughly 35 meters on each side. Thick walls surround the structure. Massive corner towers dominate the skyline. Small openings punctuate the exterior. To travelers crossing the desert, it appears defensive and intimidating. However, closer examination reveals serious contradictions. Many windows are too large for effective defense. The towers offer limited military advantages. No substantial water supply exists to withstand a prolonged siege. Archaeologists have found little evidence of permanent garrisons or military activity. Compared with genuine frontier fortresses of the Byzantine or Roman worlds, Casa Carana would have been remarkably vulnerable. This contradiction has puzzled historians for decades. If it was designed as a fortress, why does it fail to meet many requirements of military architecture? If it was not a fortress, why was it deliberately constructed to resemble one? Some researchers believe the imposing exterior served a symbolic rather than military purpose. The building may have projected power and authority to tribal leaders traveling through the region. In this interpretation, the walls functioned as political theatre rather than battlefield defences. Yet the greatest mystery lies not in the walls, but in the air flowing through them. The deserts of Jordan experience extreme environmental conditions. Summer temperatures frequently exceed 40 degrees Celsius during the day, while nights can become dramatically cooler. Managing heat inside a stone building under such conditions presents a major engineering challenge. Modern architects solve this problem using computer simulations, thermal modelling, and mechanical ventilation systems. The builders of Qasr Karna had none of these tools. Nevertheless, they created an environmental control system that continues to impress specialists today. The building contains a carefully arranged network of windows, vents, corridors, and interior spaces designed to regulate airflow. Openings were positioned to capture prevailing winds while limiting direct solar heating. The central courtyard functions as a thermal moderator, encouraging natural air circulation throughout the structure. Thick stone walls act as thermal mass. During the day, the masonry absorbs heat slowly, preventing rapid temperature increases inside the rooms. At night, the stored heat is gradually released as exterior temperatures fall. This process reduces temperature fluctuations and improves comfort without mechanical systems. Modern passive cooling research demonstrates that thick masonry walls can significantly reduce interior heat gain in arid climates. Similar principles appear in traditional desert architecture from North Africa, Persia, and the Arabian Peninsula. Yet, Qasr Karna represents one of the earliest and most sophisticated surviving examples from the Islamic world. Researchers studying traditional thermal architecture often compare such systems to modern passive building designs. Today, architects spend millions of dollars developing energy-efficient structures that rely on airflow, thermal mass, and natural cooling. The Umayyad builders achieved many of the same objectives over a millennium ago using stone, geometry, and experience. What remains unexplained is how these builders acquired such detailed environmental knowledge. No engineering manuals survive describing the calculations. No architectural blueprints explain the airflow strategy. No written records reveal how builders determined the optimal size and placement of vents. Did they inherit knowledge from Roman and Byzantine engineers? Did they adapt techniques from Persian desert architecture? Or was the design the result of generations of observation and experimentation across the arid landscapes of the Middle East? The answers remain unknown. Inside Qasr Karna, visitors encounter another unexpected feature. Many rooms contain sophisticated vaults and transitional architectural elements known as squinches. These structures transfer loads from square rooms to circular or domed ceilings. Such engineering requires an advanced understanding of force distribution and structural stability. The squinch system was not invented at Qasr Karna. Similar techniques existed in Sasanian Persia and later became common throughout Islamic architecture. Yet their appearance in an early Umayyad monument demonstrates that highly specialized engineering knowledge was already being applied at a remarkably sophisticated level. The builders successfully distributed thousands of kilograms of stone and masonry loads across walls and corners while maintaining structural integrity for more than 13 centuries. Many modern concrete buildings have failed after only a fraction of that lifespan. Qasr Karna still stands. Building a square structure may sound simple. In reality, achieving geometric accuracy across a large construction project is a difficult surveying challenge. The walls of Qasr Karna display impressive alignment and proportional consistency. Builders working in an open desert environment had to establish reference lines, right angles, elevations, and measurements without laser levels, electronic instruments, or modern surveying equipment. Ancient engineers likely relied on ropes, measuring rods, plumb bobs, and geometric techniques inherited from earlier civilizations. The mystery is not whether they could do it. The mystery is how they consistently achieved such accuracy across large projects while leaving almost no documentation of their methods. Perhaps the most debated question concerns the purpose of the structure itself. Several theories compete for acceptance. Some scholars see it as a caravanserai serving travellers along trade routes. Others interpret it as a meeting place for tribal negotiations. Some view it as a rural administrative centre. Others believe it functioned as a temporary residence for elite visitors or members of the Umayyad court. Each theory explains part of the evidence, none explains all of it. The interior layout contains reception spaces suitable for gatherings. The exterior projects authority. The location connects important regional routes, yet the building lacks certain features expected from each proposed function. This ambiguity has transformed Casa Karana into one of the most enigmatic monuments of the early Islamic era. What do you think was Casa Karana's true purpose? A fortress? A diplomatic centre? A caravan station? Or something entirely different? Share your thoughts in the comments below. Meninx, located on the southeastern coast of Djerba Island in modern-day Tunisia, was once one of the wealthiest cities in the Roman world. Yet its greatest mystery was not a palace, a temple, or a fortress. It was a technology. For centuries, Meninx produced one of the most valuable substances on Earth, Tyrian purple, a dye so expensive that Roman emperors restricted its use to the highest ranks of society. Even today, despite modern chemistry, researchers still debate how ancient craftsmen consistently produced this extraordinary colour on an industrial scale. The ruins of Meninx remained largely buried beneath sand and agricultural land for centuries. Although travellers reported ancient remains during the 19th century, systematic archaeological investigations accelerated only during the 20th and 21st centuries. Major surveys and excavations conducted by Tunisian and German teams revealed an urban centre stretching nearly 2 kilometres along the coast. Beneath the surface lay streets, baths, workshops, warehouses, villas, and evidence of one of the largest dye production industries ever discovered in the ancient Mediterranean. The first and greatest mystery of Meninx is the technology behind Tyrian purple itself. The dye was extracted from marine snails belonging primarily to the Murex family. Ancient writers such as Pliny the Elder described aspects of the process, yet their accounts remain incomplete and often difficult to interpret. Modern chemical analysis has shown that the final pigment contains brominated indigo compounds, particularly 6,6-dibromoindigo. Producing these compounds required a remarkably complex sequence of biological, chemical, and environmental reactions. The process began with the extraction of a tiny gland from each snail. The gland contained only a small amount of precursor material. Researchers estimate that thousands, and in some cases tens of thousands, of snails were required to produce a single gram of finished dye. The glands were then subjected to controlled decomposition. During this stage, enzymes triggered chemical transformations that released precursor molecules. Exposure to oxygen, temperature changes, and sunlight caused additional reactions. At certain stages, the liquid could appear yellow, green, blue, red, and finally deep purple. This is where the mystery begins. Modern laboratory experiments have repeatedly demonstrated that slight variations in temperature, fermentation time, oxygen exposure, or sunlight can drastically alter the final colour. A difference of only a few hours may shift the result from purple to blue. Yet Meninx appears to have produced relatively standardized pigments for centuries. Archaeological evidence suggests industrial-scale production rather than occasional experimentation. How ancient workers achieved such consistency without thermometers, chemical instruments, or modern scientific theory remains poorly understood. The challenge becomes even more impressive when production scale is considered. Excavations have uncovered enormous accumulations of crushed murex shells. Some deposits contain millions of shells. Similar shell mountains are known from Phoenician centres such as Tyre and Sidon, but Meninx appears to have rivaled the largest purple dye industries in the Mediterranean. If each gram of dye required thousands of snails, then the total number processed at Meninx over centuries may have reached into the hundreds of millions. The logistics behind such an operation remain difficult to reconstruct. This leads to the second mystery: resource management. Djerba is an island, and maintaining continuous access to massive quantities of marine snails would have required extensive harvesting networks. Ancient fishermen somehow avoided collapsing local populations despite centuries of exploitation. Archaeologists still debate whether Meninx relied solely on nearby waters or whether specialized supply systems brought shells from distant regions. No written records have survived to explain how this industrial ecosystem functioned. The third mystery involves industrial organization. Modern researchers increasingly view Meninx not merely as a city but as a manufacturing center. Excavations reveal evidence of workshops distributed across large sectors of the settlement. The production process generated intense odors because decomposing snail glands release sulfur compounds. Ancient authors described purple dye facilities as among the foulest smelling industries in the Roman world. Yet Meninx successfully integrated these operations into a prosperous urban environment. How city planners balanced industrial production, residential districts, trade facilities and sanitation remains only partially understood. Another unanswered question concerns water management. Dye production required substantial quantities of water for processing, cleaning and handling materials. Yet Djerba receives limited annual rainfall, typically less than 250 millimeters in many areas. Archaeological investigations have revealed cisterns, reservoirs, and hydraulic infrastructure, but researchers still debate whether these systems alone could support large-scale industry. Some scholars suggest that groundwater extraction technologies were far more sophisticated than previously assumed. Others argue that seasonal water storage systems reached efficiencies rarely appreciated in ancient engineering. The fourth mystery concerns the city's harbour. Meninx became wealthy because it connected North Africa to the wider Roman economy. Luxury textiles coloured with Tyrian purple travelled across the Mediterranean, reaching elite markets from Italy to the Near East. However, the ancient harbour itself remains elusive. Geological studies indicate that coastlines around Djerba have changed significantly over the last 2,000 years due to sedimentation and sea level fluctuations. Portions of the harbour may now lie buried beneath sediments or submerged offshore. Remote sensing surveys have identified anomalies that could represent ancient maritime infrastructure, but a complete reconstruction remains impossible. The scale of Meninx's commercial success raises further questions. During the Roman Empire, purple garments symbolized authority, wealth, and political power. Certain shades were reserved exclusively for emperors. Historical sources indicate that purple dye could command prices comparable to precious metals. Although exact values varied across time and region, ancient records consistently portray Tyrian purple as one of the most expensive manufactured products in the world. Meninx therefore occupied a strategic position within a luxury economy whose value exceeded that of many ordinary commodities. Yet surprisingly little documentation survives regarding the administration of this industry. The fifth mystery involves scientific knowledge itself. The craftsmen of Meninx clearly understood practical chemistry, even if they lacked modern terminology. They manipulated biological materials, controlled fermentation, managed oxidation reactions, and exploited photochemical processes. Their work resembles a sophisticated laboratory operation, conducted on an industrial scale. The situation invites comparison with Roman concrete, whose chemical durability still fascinates materials scientists, or the Antikythera mechanism, whose mechanical sophistication stunned modern researchers. In each case, ancient knowledge achieved results that later generations struggled to explain completely. Perhaps the most fascinating aspect of Meninx is that its technological success depended upon invisible processes. Visitors saw purple cloth, they saw wealth, they saw luxury. But the crucial transformations occurred at the molecular level. Ancient workers learned through experience how to guide reactions they could never directly observe. Long before chemistry became a science, they mastered practical methods capable of producing one of history's most coveted materials. The final mystery is the disappearance of that expertise. Meninx flourished for centuries before declining during late antiquity. Trade routes shifted, political structures changed, economic priorities evolved. Eventually the city faded, and its industrial knowledge disappeared with it. The workshops fell silent, the harbour declined, the recipes were forgotten. What remained were mountains of shells and fragments of a technology that once supplied emperors. Which mystery of Meninx fascinates you the most? Let us know your thoughts in the comments below. Rocapertiz was discovered near the village of Velo in southern France, roughly 25 kilometers northwest of Marseille. Archaeologists initially believed the site was nothing more than a small Celtic sanctuary dating to the 3rd century BCE. But as excavations expanded during the late 19th and early 20th centuries, researchers uncovered something deeply unusual: precision-carved stone pillars, engineered ceremonial platforms, and sculptures that seemed technologically out of place for Iron Age Gaul. The deeper archaeologists dug, the stranger the site became. Rocapertiz did not resemble a primitive tribal settlement. Instead, parts of it appeared closer to Mediterranean ceremonial architecture seen in Greek colonies along the coast. Even today, historians still debate whether the builders were purely Celtic, heavily influenced by Greek engineers, or part of a hybrid culture that modern history barely understands. The most infamous structures at Rocapertiz are the stone pillars carved with oval niches believed to hold real human skulls after ritual ceremonies. Ancient Greek writers described Celtic head cults in Gaul, but Rocapertiz is one of the few places where physical architectural evidence appears to support those accounts. What shocked archaeologists was not the ritual itself, but the precision of the carving. The niches were not randomly cut. Many are nearly identical in diameter and depth, suggesting standardized measurements. Several openings vary by less than a few millimeters despite being carved into limestone more than 2,200 years ago. Experimental archaeologists attempting to recreate the cuts using replica Iron Age tools discovered that maintaining such symmetry without fracturing the stone requires remarkable control and repeated measurement. Some researchers compared the craftsmanship to early Hellenistic masonry techniques found in Greek colonies around Massalia, modern Marseille. That comparison created a major controversy. Traditional history often portrays Celtic tribes of southern Gaul as fierce warriors with limited architectural sophistication. Yet Rocapertiz demonstrates a level of stoneworking far beyond that stereotype. Even stranger, the pillars appear engineered to distribute weight evenly despite having multiple hollow cavities carved into their cores. Modern structural analysis suggests the builders intentionally avoided cutting into key stress zones that could cause cracking. That implies an intuitive understanding of load distribution centuries before Roman engineering dominated the region. Among the most mysterious discoveries were several carved stone heads and seated warrior figures. Unlike the rough tribal carvings commonly associated with Iron Age Europe, these sculptures display surprisingly advanced proportions and controlled detailing. Hair patterns were carved using parallel grooves of nearly consistent spacing. Facial features show evidence of planned symmetry. Some eye sockets were drilled to almost equal depth, something extremely difficult using basic hand tools on fragile limestone. Under magnification, archaeologists identified repetitive chisel patterns suggesting specialized metal tools rather than crude stone instruments. The question became unavoidable. Where did this level of craftsmanship come from? One theory proposes direct contact with Greek artisans from nearby Mediterranean colonies. Marseille, founded by Greek settlers around 600 BCE, became one of the largest trade hubs in Western Europe. Greek ceramics and imported goods have been found throughout southern Gaul. Some historians believe Roquepertusa may represent a fusion between Celtic spiritual traditions and Mediterranean engineering knowledge. But there is a problem with that explanation. Even Greek-influenced settlements in the region rarely produce ceremonial sculptures with the same abstract yet technically disciplined style seen at Roquepertusa. The site appears culturally unique, neither fully Celtic nor fully Mediterranean. That ambiguity has fueled decades of debate. Southern France experiences violent seasonal weather changes. The Mistral wind can exceed 90 kilometers per hour, carrying dry air capable of accelerating limestone erosion. Over 2 millennia, exposed carvings should have degraded far more severely than what archaeologists see today. Yet many surfaces at Roquepertus remain unexpectedly sharp. Microscopic analysis revealed that portions of the stone may have undergone surface hardening. Some researchers suspect the limestone was treated with mineral-rich coatings or exposed to repeated heating processes that altered the outer crystalline structure. Others argue the preservation is simply geological luck, but comparisons with nearby Iron Age sites raise difficult questions. At many contemporary Celtic settlements across France and Central Europe, decorative carvings have eroded almost beyond recognition. Roquepertus, despite centuries of exposure, preserves structural edges and facial details at a much higher rate. If the builders understood methods for improving stone durability, that knowledge has been completely lost. One of the most debated elements of Roquepertus is its ceremonial gateway, a structure composed of heavy horizontal lintels supported by vertical pillars on unstable terrain. Modern reconstructions estimate some stone components weighed several tons, yet the sanctuary was built on uneven limestone foundations vulnerable to shifting and seasonal stress fractures. Normally, structures of this kind collapse quickly without advanced stabilization techniques, but Roquepertus survived for centuries before eventual destruction, likely during Roman expansion into southern Gaul around the 2nd century BCE. Engineers studying the ruins noticed something remarkable. The builders appear to have positioned the heaviest loads directly above naturally reinforced rock zones beneath the sanctuary. The arrangement reduced lateral pressure and distributed force vertically into the bedrock. This was not random construction. It suggests the builders understood principles of balance and compression at a surprisingly advanced level. Similar load management strategies would later appear in Roman arches and Greek ceremonial gateways, yet Roquepertus predates many comparable Western European examples. Some historians now argue that Iron Age Celtic engineering has been dramatically underestimated. Another mystery involves the orientation of the sanctuary itself. Several archaeologists observed that parts of the structure align unusually well with the summer solstice sunrise. During certain periods of the year, sunlight may have passed directly through ceremonial openings and illuminated central ritual areas. If intentional, this would place Roquepertusa among a global pattern of ancient ritual sites linked to astronomy, including Stonehenge in Britain, Nabta Playa in Egypt, and multiple Greek temple complexes aligned to solar events. However, proving astronomical intent is extremely difficult because much of Roquepertus was destroyed long ago. The surviving ruins are incomplete, leaving researchers divided. Still, the possibility remains unsettling. If Celtic builders in southern Gaul incorporated astronomical calculations into ritual architecture, Their scientific understanding may have been far more sophisticated than ancient Roman writers ever acknowledged. Do you think Rossigpertusa was simply a Celtic sanctuary, or evidence of a forgotten civilization far more advanced than history admits? Share your thoughts in the comments below. Yoshinogari is a vast archaeological site in Saga Prefecture, Kyushu, Japan. More than 2,000 years ago, it became one of the largest and most sophisticated settlements of the Yayoi period. Yet beneath its reconstructed watchtowers and defensive moats lies a mystery that continues to challenge archaeologists today. How did a society with relatively simple tools develop engineering, metallurgy, urban planning, and social organization on a scale that seemed centuries ahead of its time? The modern story of Yoshinogari began unexpectedly in 1986, when land was being prepared for industrial development. Archaeologists conducting preliminary surveys discovered traces of ancient ditches, post holes, and pottery. What initially appeared to be a routine excavation soon expanded into one of the largest archaeological investigations in Japanese history. Excavations revealed a fortified settlement covering more than 40 hectares, complete with defensive systems, ceremonial structures, elite tombs, workshops, and thousands of artifacts dating primarily between the 3rd century BCE and the 3rd century CE. The discovery transformed understanding of early Japanese civilization. For decades, many historians viewed Yayoi communities as relatively small agricultural villages. Yoshinogari revealed something very different, displaying evidence of centralized authority, long-distance trade, advanced engineering, and social stratification. More importantly, it exposed several technological mysteries that remain unresolved. The first mystery involves the enormous defensive system surrounding the settlement. Excavations uncovered multiple concentric moats and wooden palisades encircling key areas of the community. Some moats measured several meters wide and deep enough to create significant defensive obstacles. Constructing such fortifications required moving vast quantities of soil using tools made primarily from wood, stone, and limited iron implements. Researchers estimate that excavating even a single large defensive ditch would have required tens of thousands of labor hours. Similar large-scale earthworks are known from Iron Age Europe, including Celtic oppida such as Bibracte in France, and from early Chinese fortified settlements. However, Yoshinogari demonstrates that comparable organizational capabilities existed in Japan much earlier than previously believed. The question is not whether the moats could be built, because they clearly were. The mystery is how a society without written administrative records coordinated such a massive workforce. Who planned the construction? How was labor organized? How were food supplies managed during major building projects? Archaeologists have found evidence of centralized storage facilities, suggesting some form of political authority, but the exact administrative system remains unknown. The second mystery concerns the enormous wooden towers discovered within the settlement. Archaeologists identified post holes over 1 meter in diameter, indicating that some structures were supported by massive timber columns. Reconstructions suggest that certain towers may have reached heights of 10 to 15 meters. Building structures of this scale required far more than simply cutting down trees. Engineers had to select suitable timber, transport heavy logs, excavate stable foundations, and erect columns weighing several tons. Without cranes, steel tools, or modern lifting equipment, the builders achieved remarkable structural stability. Japanese traditional carpentry later became famous for its sophisticated joinery techniques. Some researchers believe Yoshinogari may represent an early stage in the development of these engineering traditions. Yet the precise construction methods remain uncertain, as no detailed instructions survived and the knowledge vanished with the people who created it. The third mystery involves urban planning. Unlike many prehistoric settlements that developed organically, Yoshinogari exhibits signs of deliberate spatial organization. Residential zones, ceremonial areas, workshops, storage facilities, cemeteries, and defensive structures appear carefully arranged. This level of planning resembles development seen in ancient Chinese centers such as Erlitou or early Korean fortified settlements. The arrangement suggests that builders understood concepts of zoning, security, logistics, and social hierarchy. Satellite imagery, aerial surveys, and excavation maps indicate that movement throughout the settlement may have been intentionally controlled through gates, pathways, and enclosed compounds. Such planning implies a sophisticated understanding of social management and security. Yet archaeologists still debate whether these concepts emerged independently within Japan or were influenced by technological and cultural exchanges with mainland Asia. The fourth mystery, and perhaps the most fascinating, involves metallurgy. Yoshinogari has produced numerous bronze and iron artifacts, including weapons, agricultural tools, ritual objects, and mirrors. These discoveries reveal that the community possessed access to some of the most advanced technologies of its era. The transition from stone tools to metal fundamentally changed human history. Iron tools dramatically increased agricultural productivity, while bronze objects became symbols of status, ritual authority, and political power. Control over metallurgy often translated directly into control over society. What makes Yoshinogari remarkable is the speed with which metal technology appears to have spread throughout the region. Bronze mirrors discovered at the site resemble examples found in Han Dynasty China. Certain bronze ceremonial bells, known as dotoku, reflect technological traditions that likely originated on the Asian mainland before being adapted locally. Iron blades and agricultural implements demonstrate knowledge of metalworking that was previously thought to have developed more gradually. The central mystery concerns the source of this knowledge. Did Yoshinogari import finished products from China and Korea? Did immigrant craftsmen bring metallurgical expertise across the sea? Or did local specialists rapidly master foreign technologies and develop their own production systems? Archaeological evidence supports elements of all three possibilities. The distance between northern Kyushu and the Korean peninsula is approximately 200 kilometers at its narrowest crossing. Maritime routes connected these regions long before written Japanese history began. Artifacts discovered at Yoshinogari demonstrate participation in extensive trade networks extending across East Asia. However, trade alone does not explain everything. Several excavations have uncovered evidence suggesting local metalworking activity. Fragments of molds, traces of metal processing, and workshop areas indicate that at least some manufacturing occurred within the settlement itself. Yet complete smelting facilities remain surprisingly scarce. This creates a technological puzzle. Producing bronze requires precise control of copper and tin ratios, while producing usable iron is even more demanding. Iron ore must be heated to temperatures exceeding 1,100 degrees Celsius under carefully controlled conditions. Variations in temperature, oxygen supply, and furnace design can dramatically affect the final product. Even in many parts of Europe, mastering iron production required centuries of experimentation. The Celtic world, the Roman Empire, and Han China all invested enormous resources into metallurgical development. How then did a society at the edge of East Asia acquire such capability so rapidly? Some researchers propose that specialized craftsmen migrated directly from the Korean peninsula, carrying technical knowledge with them. Others suggest that technological transfer occurred through generations of trade and cultural interaction. Neither explanation fully accounts for the archaeological evidence. Perhaps the greatest mystery is the disappearance of the knowledge itself. The bronze casters, furnace builders, or specialists and metal workers who possessed these skills left behind almost no written explanations. Their products survived, but their methods largely vanished. The fifth mystery concerns the elite cemetery discovered at the site. Hundreds of burials have been excavated, but some individuals received dramatically different treatment than others. Certain graves contain bronze mirrors, weapons, beads, and prestigious imported goods. These burial differences indicate a highly stratified society. This raises another unresolved question. How did social inequality emerge so quickly? For thousands of years, many Jomon communities appear to have maintained relatively egalitarian social structures. Yet, within the Yayoi period, powerful elites emerged who could command labor, control trade, and accumulate wealth. Some archaeologists argue that rice agriculture generated economic surpluses that enabled political centralization. Others believe control over metallurgy and long-distance trade created new power structures. The evidence remains incomplete. Yoshinogiri is often linked to the legendary kingdom of Yamatai, one of Japan's greatest archaeological mysteries. Ancient Chinese records describe Yamatai as a powerful state ruled by Queen Himiko in the 3rd century CE. Because of its large size, strong defenses, elite tombs, and signs of centralized rule, some scholars believe Yoshinogiri may have been a major center of Yamatai. However, no direct evidence confirms this connection, and the true location of Yamatai remains unknown. In northern Tunisia, approximately 50 kilometers south of ancient Carthage, lies the site of Zaghouan. It became famous not because of a lost palace, temple, or royal tomb, but because it served as the source of one of the largest hydraulic engineering systems ever built by the Roman Empire. Archaeological investigations conducted during the 19th and 20th centuries revealed that the mountain springs of Zaghouan supplied water to Carthage through an aqueduct stretching approximately 132 kilometers. Even today, large sections of the system remain visible, making it one of the longest surviving Roman aqueducts in existence. At first glance, the ruins seem straightforward. Water emerged from mountain springs, entered channels, and flowed toward a city. Yet the more researchers studied the system, the more questions emerged. How did engineers nearly 2,000 years ago construct a gravity-powered water network across mountains, valleys, unstable terrain, and seismic zones without modern surveying equipment? Why does some of the engineering knowledge behind the project appear comparable to techniques that would not be fully replicated until many centuries later? The greatest mystery begins with a simple fact. Water naturally flows downhill. For a gravity-fed aqueduct to function, engineers must maintain a carefully controlled gradient throughout the entire route. If the slope becomes too steep, the water gains destructive velocity. If it becomes too shallow, flow slows dramatically or stops entirely. Modern engineers accomplish this task using satellite positioning, laser measurement systems, drones, and computer modeling, but Roman engineers possessed none of these tools. Yet the Zaghouan aqueduct maintained a functional gradient across approximately 132 kilometers of highly varied terrain. In some sections, the average slope may have been only a few tens of centimeters per kilometer. To appreciate the difficulty, imagine building a channel from one side of a major metropolitan region to another, while maintaining a nearly perfect downward angle the entire distance. A measurement error of only a few meters accumulated over the route could compromise the system. Roman writers mention instruments such as the chorobates and groma, but surviving descriptions are incomplete. Archaeologists still debate how survey teams achieved such remarkable precision across distances, exceeding those of many modern infrastructure projects. The challenge becomes even more impressive when compared with other famous Roman aqueducts. The Aqua Claudia in Rome stretched approximately 69 kilometers, while the Pont du Gard system in southern France covered around 50 kilometers. Zaguen's network was considerably longer, requiring extraordinary planning and coordination. One of the most fascinating structures at Zaguen is the so-called water temple. At first glance, it appears religious. The semicircular facade, columns, niches, and decorative architecture resemble a ceremonial monument dedicated to water deities. Yet beneath the elegant appearance lies something far more practical. The structure functioned as a sophisticated hydraulic collection facility where multiple mountain springs converged before entering the aqueduct system. Engineers effectively transformed a natural geological environment into a controlled water processing station. Researchers estimate that the springs could produce thousands of cubic meters of water per day. Before entering the main channel, sediments had to settle and flow rates had to be regulated. This raises an intriguing question. How did Roman engineers identify these specific spring systems as reliable long-term water sources? Modern hydrogeologists use drilling equipment, satellite imagery, groundwater mapping, chemical analysis, and computer simulations, whereas Roman builders relied on observation, experience, and methods that remain only partially understood. The selection proved remarkably successful, as nearly 2,000 years later the springs continue to produce water. The route between Zaguen and Carthage was far from ideal. The aqueduct crossed valleys, hills, changing soil conditions, and regions affected by tectonic activity. In several areas, engineers had to construct elevated arcades, carrying the water channel high above the surrounding terrain. Many surviving arches remained standing after nearly 20 centuries, creating another engineering puzzle. How did Roman builders calculate structural loads without modern mathematics, finite element analysis, or reinforced concrete? The tallest surviving sections originally reached heights exceeding 20 meters. Each arch transferred forces through carefully shaped stone blocks, distributing weight into foundations below. The principles involved resemble concepts taught in modern structural engineering, yet the calculations were performed without computers, calculators, or standardized engineering textbooks. Comparisons with other ancient projects make the achievement even more remarkable. The Great Pyramid of Giza demonstrates extraordinary stone placement, while the Parthenon demonstrates advanced architectural precision. The Zaguen system demonstrates something different: large-scale infrastructure engineering operating continuously across an entire landscape. Unlike a temple or monument, an aqueduct had to function every day. One reason sections of the aqueduct survived for so long involves Roman hydraulic concrete. Many channels were lined with waterproof materials known as *opus signinum *. This mixture incorporated crushed ceramics, lime, and other components that created durable water-resistant surfaces. Modern materials scientists have spent decades studying Roman construction materials because some ancient structures appear unusually resistant to aging. In marine environments, Roman concrete has survived nearly 2 millennia of exposure, while some modern concrete structures require major repairs after only several decades. The exact performance mechanisms remain an active area of scientific research. At Zaguen, waterproof channels successfully transported water over enormous distances while limiting leakage. This required not only advanced material knowledge, but also strict quality control during construction. The mystery is not whether Roman builders understood their materials. The mystery is how they developed such effective formulations through experimentation alone. Transporting water 132 kilometers was only half the challenge. Once the water reached Carthage, it entered one of the largest storage systems in the Roman world. The famous La Malga cisterns could store approximately 50 to 60 million litres of water. Massive vaulted chambers stretched across the site, forming a giant reservoir complex. The scale was extraordinary. An Olympic swimming pool contains roughly 2.5 million litres of water, meaning the La Malga system held the equivalent of around 20 Olympic pools. Yet archaeologists still debate important aspects of the distribution network. Exactly how was water prioritized between households, fountains, baths, workshops, and government facilities? How were seasonal fluctuations managed? How was pressure controlled across different districts? Parts of the network have been identified, but a complete understanding remains elusive. The city consumed enormous quantities of water, yet the operational details behind this urban machine remain partially hidden beneath modern development and centuries of destruction. What do you think was the most impressive achievement of the Zaguan aqueduct? The 132-kilometre survey, the hydraulic engineering, or the lost knowledge behind its construction? Let us know your thoughts in the comments below. Yingzhou, located near modern-day Anyang in Henan Province, China, should not have existed at the level of sophistication archaeologists found. More than 3,000 years ago, this city served as the last capital of the Shang dynasty, yet buried beneath its soil were technologies, manufacturing systems, and administrative capabilities that in some cases rivaled or exceeded those of many contemporary civilizations. The greatest mystery is not that Yingzhou existed. The mystery is how a Bronze Age society developed industrial-scale production, advanced metallurgy, a fully mature writing system, and a centralized network capable of managing enormous resources centuries before many comparable societies elsewhere. The rediscovery of Yingzhou began in 1899 when scholar Wang Yirong noticed strange symbols carved onto so-called dragon bones sold in Chinese medicine shops. These bones were later identified as ancient oracle bones containing the earliest known form of Chinese writing. Systematic excavations began in 1928 under archaeologist Li Ji of the Institute of History and Philology. Over the following decades, archaeologists uncovered palace foundations, royal tombs, workshops, sacrificial pits, and more than 150,000 oracle bone fragments. What emerged was not merely a lost city but evidence of one of the most technologically advanced civilizations of the Late Bronze Age. The first and perhaps greatest mystery of Yingzhou is its bronze casting technology. Bronze production was common throughout the ancient world, but the scale and complexity achieved at Yingzhou remain astonishing. During the Shang dynasty, craftsmen produced massive ritual vessels weighing hundreds of kilograms while maintaining extraordinary decorative precision. Some vessels display intricate patterns covering every surface, including deep relief designs that would challenge even experienced modern metal workers. What makes this achievement particularly mysterious is the casting method itself. Unlike ancient Egypt, Mesopotamia, and later Greece, which primarily employed variations of lost wax casting, Shang craftsmen relied on a technique known as piece mold casting. This process required artisans to first create a clay model, then build multiple molds around it, remove the molds, carve detailed decorations into the mold surfaces, reassemble them perfectly, and finally pour molten bronze into the cavity. The challenge becomes clear when examining the physics involved. Bronze melts at temperatures exceeding 950 degrees Celsius. Large vessels required enormous quantities of molten metal to be poured rapidly and evenly. Any slight misalignment between mold sections could ruin the entire object. Thermal expansion, shrinkage during cooling, trapped gases, and uneven metal flow all presented serious engineering obstacles. Yet archaeological evidence suggests Shang workshops consistently achieved remarkable success. One famous example is the Simu Ding discovered near Yingxu in 1939. Weighing approximately 832 kilograms, it remains the heaviest ancient bronze vessel ever found in China. Producing such an object would have required more than 1 ton of molten metal and an exceptionally stable casting environment. Even modern engineers debate exactly how Shang craftsmen controlled temperature gradients and metal distribution during the casting process. Experimental archaeology has successfully replicated smaller objects, but many questions remain regarding the production of the largest vessels. Comparisons with other Bronze Age civilizations only deepen the mystery. During the 13th century BC, when Yingxu flourished, many Mediterranean societies produced bronze objects measured in kilograms. The largest Shang ritual vessels often exceeded those weights by an order of magnitude while incorporating significantly more complex decorative programs. The technological gap is difficult to explain solely through gradual development. The second mystery concerns the enormous supply chain required to sustain this bronze industry. Chemical analyses of Shang bronzes reveal mixtures of copper, tin, and lead in carefully controlled proportions. Copper isotopic studies suggest that ores originated from multiple mining regions located hundreds of kilometers from Yingxu. Maintaining continuous access to these resources would have required organized extraction, transportation, storage, and distribution systems. Archaeologists estimate that thousands of tons of metal were consumed throughout the Shang period. Such production implies the existence of large mining operations, skilled labor forces, and administrative oversight. Yet the full extent of this network remains unknown. Many of the mines that supplied Yingxu have not been conclusively identified, creating a significant gap in our understanding of how the Shang economy functioned. The third mystery involves the sudden appearance of a mature writing system. The oracle bone inscriptions discovered at Yingxu represent the earliest substantial corpus of Chinese writing ever found. More than 150,000 fragments have been recovered containing approximately 5,000 distinct characters. Of these, scholars have deciphered roughly 1/3 with reasonable confidence. The problem is that the system already appears highly developed. The inscriptions include phonetic components, semantic elements, grammatical structures, personal names, military records, agricultural reports, astronomical observations, and ritual instructions. Writing systems generally evolve through long transitional phases, leaving behind simpler intermediate forms. At Yingxu, however, the script emerges in the archaeological record already functioning as a sophisticated administrative tool. This raises a profound question. Where are the earlier stages? A fully mature writing system does not appear overnight. Many researchers believe that centuries of written tradition must have preceded the inscriptions found at Yingxu, yet definitive evidence for those earlier phases remains elusive. The fourth mystery centers on the oracle bone divination system itself. To modern observers, oracle bone rituals may appear purely religious. In reality, they constituted one of the most organized information management systems of the ancient world. Shang diviners drilled precise pits into turtle shells or animal bones and applied heat until cracks formed. Questions regarding warfare, harvests, weather, royal births, hunting expeditions, and political decisions were then interpreted from the resulting patterns. What is remarkable is the degree of standardization. The placement of pits, the methods of heating, the recording of questions, and the documentation of outcomes followed consistent procedures. Thousands of inscriptions effectively created a database spanning generations. Some historians compare this system to an early form of bureaucratic record-keeping, preserving information on an unprecedented scale for the Bronze Age. The fifth mystery involves astronomy. Numerous oracle bone inscriptions record eclipses, planetary movements, lunar phases, and unusual celestial events. These observations demonstrate that Shang scholars tracked astronomical cycles with surprising accuracy. Certain inscriptions correspond closely with eclipses that modern astronomers can calculate retrospectively. Such precision required systematic observation over long periods. Yet archaeologists have found little evidence for large observatory complexes comparable to those known from later civilizations. How Shang astronomers accumulated and preserved their knowledge remains poorly understood. The sixth mystery emerged dramatically in 1976 with the excavation of the tomb of Fu Hao. Unlike most royal Shang burials, which had been looted centuries earlier, Fu Hao's tomb remained largely intact. Archaeologists uncovered more than 1,900 artifacts, including nearly 500 bronze objects, hundreds of jade pieces, ivory carvings, stone tools, weapons, and thousands of cowrie shells used as currency. Oracle bone inscriptions identify Fu Hao as both a queen and a military commander. Records suggest she led campaigns involving thousands of soldiers. If these texts are interpreted correctly, the Shang state possessed military capabilities far larger and more sophisticated than previously assumed. Yet many details regarding recruitment, logistics, command structures, and battlefield organization remain unknown. What do you think is the greatest mystery of Yingzhou? The giant bronze vessels, the lost origins of Chinese writing, or the knowledge that vanished with the Shang dynasty? Steam still rises from the water every single day beneath the city of Bath in southwestern England. More than 2,000 years after Roman engineers first enclosed the spring with stone, the water continues to emerge from the earth at nearly 46 degrees Celsius, pushing over 1 million litres to the surface every day. Modern geothermal spas use electric pumps, pressure sensors, reinforced concrete, and computerized flow systems to maintain stable operation. The Roman baths used none of them, and yet the system survived. What makes the Roman baths extraordinary is not simply their age. It is the possibility that Roman engineers understood underground heat, mineral corrosion, structural pressure, airflow, and water control at a level historians once believed impossible for the ancient world. The site was built around a natural hot spring during the 1st century AD, shortly after the Roman conquest of Britain. Archaeologists believe Roman surveyors identified the spring because of constant steam rising through the marshlands of the River Avon Valley. Excavations beginning in the late 19th century uncovered massive submerged foundations, collapsed chambers, lead pipelines, and one of the most sophisticated thermal complexes ever discovered in the Roman Empire. But the deeper archaeologists dug, the stranger the engineering became. The first mystery is the spring itself. The hot water beneath Bath is created by an unusually deep geothermal cycle. Rainwater seeps underground through limestone faults and travels down nearly 3 to 5 kilometers beneath the surface. There, geothermal heat warms the water before underground pressure forces it upward through fractures in the rock. Modern hydrogeologists estimate this process can take thousands of years for a single drop of water to complete. What remains difficult to explain is how Roman engineers located the most stable pressure zone without modern geological tools. If the retaining walls had been placed incorrectly, sediment could have blocked the spring, pressure could have collapsed the chambers, or temperature fluctuations could have destabilized the entire system. Instead, the Romans constructed a reservoir lined with massive lead sheets and stone blocks, capable of containing constant thermal expansion for centuries. Even today, engineers studying geothermal systems compare Bath to passive thermal regulation used in modern spa infrastructure. The second mystery involves the materials. The water flowing through the Roman baths is rich in dissolved minerals including calcium sulfate, sodium chloride, and magnesium compounds. Under modern conditions, mineral-rich thermal water rapidly destroys pipes and concrete through scaling and chemical corrosion. Many modern geothermal facilities require continuous maintenance to prevent mineral buildup from choking entire systems. Yet large portions of the Roman baths survived nearly 2 millennia. Scientists analyzing Roman mortar discovered that the builders used mixtures containing lime, crushed brick, and volcanic ash in carefully balanced proportions. These mixtures created pozzolanic reactions, chemical processes that continue strengthening the concrete when exposed to water. In some microscopic studies, Roman concrete exposed to seawater or thermal water actually became more chemically stable over time. This directly contrasts with modern Portland cement, which often weakens after prolonged exposure to hot mineral-rich water. At Bath, the survival of underground walls exposed to heat and flowing minerals for nearly 2,000 years remains one of the strongest examples of Roman material engineering outperforming many modern equivalents. The third mystery lies beneath the floor. The Roman baths operated using a hypercore system, essentially a giant ancient heating network hidden under stone surfaces. Workers maintained furnaces that pushed hot air beneath elevated floors supported by hundreds of brick pillars. Heat traveled through hollow wall channels before exiting through roof vents. The result was astonishingly advanced. The floors remained warm, moisture levels stayed controlled, and steam circulated through different chambers with remarkable consistency. Temperature could be adjusted between hot, warm, and cold rooms in ways surprisingly similar to modern climate-controlled spas. Engineers today recognize the same principles in radiant floor heating and HVAC airflow systems involving convection, pressure circulation, thermal distribution, and humidity management. What makes the Roman system remarkable is that it functioned entirely without electricity or mechanical pumps. The entire complex relied purely on geometry, airflow, and thermal pressure gradients. Some researchers argue the Romans may have developed practical engineering knowledge of heat behavior centuries before formal thermodynamics existed as a science. Another major mystery involves lead. Large sections of Roman plumbing used lead pipes, a fact that has puzzled historians for decades. Modern medicine identifies lead as highly toxic, especially through drinking water systems. Yet Roman cities operated extensive lead-based plumbing networks across Europe for centuries. At Bath, mineral-rich water may hold the answer. Studies suggest the high calcium content of the spring water quickly formed thick mineral coatings inside the pipes, dramatically reducing direct contact between water and lead surfaces. Similar effects are observed in some modern water systems where carbonate deposits create protective barriers inside old pipelines. This accidental chemical protection may explain why catastrophic mass poisoning evidence remains surprisingly limited in many Roman settlements. Even so, debate continues among archaeologists, toxicologists, and historians. Some argue chronic low-level exposure still affected Roman populations in ways difficult to detect today. The architecture itself presents another puzzle. Roman bath chambers generated enormous amounts of steam every day. Constant condensation should have weakened ceilings, destabilized stone joints, and accelerated structural decay. Yet many arches and vaulted spaces remained standing for centuries. Researchers studying Roman vault geometry discovered that curved ceilings may have been intentionally designed to redirect condensation and distribute moisture evenly across surfaces. The arches also disperse structural stress while allowing rising hot air to circulate naturally through upper chambers. Modern sauna complexes use remarkably similar airflow principles. but Roman builders achieved this using only stone, fired clay, lime mortar and geometric calculations. No steel reinforcement existed. No computer simulations guided the construction. Everything depended on experience, observation and mathematical intuition. The baths also reveal an unsettling connection between engineering and religion. The complex was dedicated to Sulis Minerva, a fusion of a local Celtic goddess and the Roman goddess Minerva. To ancient visitors, the spring was not merely geothermal activity, it was sacred. Excavations uncovered hundreds of curse tablets buried in the water. These thin sheets of lead were inscribed with requests for divine punishment against thieves, rivals, or traitors. Many were intentionally thrown into the deepest parts of the spring where water pressure was strongest. To the Romans, the rising thermal waters may have represented a gateway between worlds. This blending of advanced engineering with supernatural belief appears repeatedly across ancient civilizations. The Maya aligned temples with astronomical cycles. Egyptian pyramids integrated celestial orientation into monumental architecture. At Bath, hydraulic engineering became inseparable from ritual power. One of the most surprising discoveries came from modern scanning technology. Laser mapping and underground surveys revealed that much of the Roman hydraulic infrastructure extended deeper and farther than earlier archaeologists realized. Hidden drainage tunnels, overflow channels, and pressure release systems suggest the complex was designed not only to transport water, but also to survive long-term geological instability. This level of planning resembles modern civil engineering far more than traditional ancient construction. Comparisons with other Roman sites only deepen the mystery. At Pompeii Archaeological Park, volcanic ash preserved water systems capable of regulating fountains and baths across an entire city. At Aqueduct of Segovia, stone arches transported water over 15 kilometers without mortar. At Chedworth Roman Villa, Hippocaust systems maintained heated floors through British winters nearly 2,000 years ago. But Bath combined all of these technologies together: geothermal extraction, thermal regulation, hydraulic engineering, structural moisture control, and mineral-resistant construction. Few ancient sites demonstrate such an integrated understanding of environmental engineering. Longshan Temple, standing in the heart of Taipei, Taiwan, is not supposed to be a mystery. Built in 1738 by settlers from Fujian during the Qing dynasty, it is one of the most studied temples in East Asia. Millions of visitors walk through its gates every year. Historians know who built it. Engineers can measure every beam and pillar. Yet the deeper researchers investigate the temple, the more they encounter a disturbing question. How did craftsmen nearly 3 centuries ago create architectural and material technologies that continue to challenge modern understanding? The story begins in Taipei Basin, northern Taiwan. Longshan Temple was established by immigrants from Quanzhou, Fujian, who brought with them centuries of traditional Chinese construction knowledge. Over time, the temple survived earthquakes, typhoons, fires, political upheavals, and even aerial bombing during World War II. In 1945, Allied aircraft bombed parts of Taipei, damaging sections of the temple, yet the main sanctuary survived. Today, despite repeated disasters, the structure remains one of the most important examples of traditional Chinese temple engineering in East Asia. What makes Longshan Temple extraordinary is not merely its beauty. It is the hidden technology embedded within every beam, roof, column, and ornament. The first mystery involves its remarkable resistance to earthquakes. Taiwan sits on the boundary between the Philippine Sea Plate and the Eurasian Plate, making it one of the most seismically active regions on Earth. Modern Taiwan experiences thousands of measurable earthquakes every year. Major earthquakes such as the 1999 Chi-Chi earthquake, which registered magnitude 7.6, demonstrated the devastating power of the island's geology. Yet traditional temple structures built centuries earlier often display resilience that surprises engineers. Unlike modern concrete buildings, Longshan Temple relies primarily on timber framing. The structure functions as a flexible system rather than a rigid one. Instead of resisting seismic energy directly, the building absorbs and redistributes it. Massive wooden columns transfer loads through an intricate network of beams and brackets. During ground movement, these connections can shift slightly without catastrophic failure. Researchers frequently compare such systems to modern seismic isolation technologies. Contemporary skyscrapers often require expensive dampers, tuned mass systems, and computer-designed flexibility mechanisms. Longshan Temple's builders achieved a similar principle using only wood, geometry, and experience. No surviving documents explain precisely how these craftsmen calculated load distribution. There were no structural engineering equations, no computer simulations, and no digital models. Yet, the results continue to perform remarkably well under seismic stress. The second mystery concerns the temple's astonishing joinery system. Thousands of wooden components are connected without relying on modern metal fasteners. Traditional Chinese carpentry employs mortise and tenon joints, allowing pieces to interlock with extraordinary precision. At Longshan Temple, many connections appear almost seamless. Modern architects often compare this system to three-dimensional puzzles. Every component must fit perfectly while simultaneously carrying weight from the massive roof above. A single error can affect the stability of an entire section. Yet craftsmen working with hand tools achieve tolerances that remain impressive even by modern standards. Perhaps most fascinating is the disappearance of the knowledge itself. Many traditional construction techniques were transmitted orally through apprenticeships rather than written manuals. As generations passed, portions of this knowledge gradually vanished. Restoration teams today frequently rely on surviving master craftsmen because historical records alone cannot fully explain the construction process. The third mystery rises above the temple itself. Longshan Temple's roof is among the most recognizable architectural features in Taiwan. The sweeping curves create a silhouette that appears almost impossible. These roofs are not merely decorative. Their shape serves multiple engineering functions simultaneously. Taipei receives approximately 2,400 millimeters of rainfall annually. Typhoons regularly bring intense wind and water. The curved roof channels rain water efficiently away from vulnerable structural elements. At the same time, the design helps distribute loads across supporting columns and beams. Modern wind tunnel testing on traditional East Asian roofs suggests that their geometry may reduce certain aerodynamic stresses. Yet no evidence indicates that 18th century builders possessed formal aerodynamic theories. Through centuries of experimentation, they developed forms that perform surprisingly well under harsh environmental conditions. The fourth and perhaps greatest mystery involves the ceramic sculptures covering the roof. Dragons, phoenixes, immortals, warriors, mythical creatures and religious figures stretch across ridges and corners in extraordinary detail. From a distance, these decorations appear artistic. Under closer examination, they become technological enigmas. The rooftop ceramic sculptures endure some of the harshest conditions imaginable. They're exposed continuously to ultraviolet radiation, tropical heat, humidity, acid rain, typhoon-force winds, and sudden temperature changes. Many modern construction materials struggle under such conditions, yet numerous traditional ceramic elements survive for decades and sometimes centuries. The question is simple: how were they made? Ancient craftsmen possessed no electron microscopes, no spectrometers, and no industrial laboratories. Nevertheless, they developed ceramic recipes capable of producing remarkable durability. The clay had to be carefully selected. Mineral composition mattered enormously. The firing temperature needed precise control. Even small variations could cause cracking, deformation, or rapid deterioration. Studies of traditional Chinese ceramics reveal firing temperatures often exceeding 1,000 degrees Celsius. Achieving and maintaining such temperatures consistently required sophisticated kiln management. Fuel selection, airflow control, chamber design, and firing duration all influenced the final product. What remains unclear is how craftsmen optimized these variables through experience alone. Modern ceramic engineers rely on extensive laboratory testing to develop durable materials. Historical artisans achieved comparable outcomes using observational knowledge accumulated over generations. Some rooftop dragons contain hundreds of individual components assembled into a single sculpture. The complexity resembles modular engineering systems. Each piece must survive thermal expansion, moisture exposure, and structural movement while maintaining visual integrity. Researchers frequently compare these ceramic traditions to the lost Roman concrete formula. Both represent technologies that worked exceptionally well, yet whose full developmental pathways remain partly hidden. We can analyze the final products, but understanding exactly how ancient craftsmen discovered these solutions remains difficult. The fifth mystery lies in the temple's stone and wood carvings. Longshan Temple contains some of the most elaborate decorative work in Taiwan. Dragons emerge from columns. Layers of figures overlap within impossibly deep reliefs. Flowers, animals, clouds, and mythological scenes intertwine across surfaces. Producing such detail requires extraordinary spatial understanding. Modern workshops often use computer-controlled machinery to achieve comparable complexity. Historical artisans relied entirely on hand tools. The precision becomes even more remarkable when considering the scale. Certain carvings extend across large architectural elements while maintaining consistent proportions. Errors could not simply be erased and restarted. Each cut permanently altered the material. Archaeologists and art historians continue debating how craftsmen organized these projects. Did they use full-scale templates? Did master builders memorize proportions? Were secret measurement systems passed through guild traditions? Definitive answers remain elusive. What do you think is the greatest mystery of Longshan Temple? Its earthquake-resistant wooden structure, its precision joinery, or the ceramic sculptures that have survived centuries of extreme weather? Share your thoughts in the comments below. Wall of Romulus was uncovered through excavations around Rome's Palatine Hill, the legendary birthplace of the city itself. Archaeologists investigating layers beneath later Roman structures found sections of massive volcanic stone fortifications dating back to the 8th century BCE, the same era traditionally linked to Romulus. What shocked researchers was not only the age of the wall, but the sophistication hidden inside it. The structure appeared far too advanced for what historians once believed was merely a small tribal settlement beside the Tiber River. The surviving remains suggest an organized defensive barrier built with carefully fitted blocks of volcanic tuff, some weighing several hundred kilograms each. Carbon dating from surrounding organic material and ceramic fragments placed portions of the construction around 730–720 BCE. That timeline places the engineering of the wall centuries before Rome became a dominant Mediterranean power. Compared to many early Italic settlements of the same period, the Wall of Romulus appears unusually strategic, unusually durable, and unusually precise. What began as a routine excavation quickly evolved into one of the greatest engineering mysteries of early Roman civilization. One of the first mysteries surrounding the Wall of Romulus involves the stonework itself. The wall was built primarily from volcanic tuff quarried from the hills surrounding Rome. Tuff is relatively soft immediately after extraction, but hardens over time when exposed to air. Ancient Roman builders appear to have understood this property in extraordinary detail. Several surviving blocks show flat contact surfaces with the deviations measuring only a few millimeters. For an 8th century BCE society using primitive bronze and early iron tools, such precision is difficult to explain. In some sections, the stones interlock tightly enough that even modern blades struggle to pass between them. Archaeologists compared the fitting techniques to later Etruscan and even Incan polygonal masonry. Yet the Wall of Romulus predates many of those advanced traditions. Some researchers argue the builders may have used abrasive volcanic sand combined with water and repetitive grinding methods, rather than relying solely on chisels. Others believe wooden frames and weighted lever systems were used to stabilize cuts with surprising accuracy. The real mystery is not merely that the stones were shaped, but that they were shaped consistently across large defensive sections without modern geometry, lasers or steel tools. Compared to other settlements in Italy during the same period, Rome's earliest fortification appears technologically ahead of its neighbors by generations. Rome was not built on ideal terrain. The city developed over layers of volcanic ash, clay, and unstable sediment near the Tiber River. Structures built on such ground usually crack, tilt, or collapse over centuries. Yet portions of the Wall of Romulus survived for nearly 2,700 years. Excavations revealed something unexpected beneath the visible stone layers: a primitive shock-absorbing foundation system. Instead of placing stones directly onto solid earth, the builders created layered beds of compacted gravel, fragmented tuff, and drainage gaps. These gaps allowed water to escape while distributing pressure more evenly across unstable terrain. Modern engineers studying the structure noticed similarities to seismic mitigation principles used in later Roman roads and even some modern earthquake-resistant foundations. Laboratory analysis of surviving sublayers showed evidence of deliberate grading in particle size. Larger fragments were placed lower, while smaller compacting materials were layered above. This reduced soil movement and prevented catastrophic shifting during seasonal flooding. The engineering resembles systems later perfected in Roman roads such as the Via Appia, yet the Wall of Romulus predates those achievements by centuries. Some experts believe early Roman builders may have gained practical geological knowledge through repeated flood disasters around the Tiber Valley. Others argue the techniques were inherited from the Etruscans, whose engineering abilities remain partially mysterious themselves. Either way, the foundation system suggests an understanding of terrain mechanics far beyond what historians once expected from early Rome. Another mystery lies in the volcanic tuff itself. Modern geological studies found that certain sections of the wall used high zeolite tuff, a material naturally resistant to moisture and thermal stress. Zeolites are microporous minerals capable of trapping water and reducing long-term cracking. The Romans could not have known the chemistry scientifically, yet they consistently selected stone from quarries with unusually durable mineral compositions. Over centuries, exposure to air triggered chemical hardening reactions within the volcanic material. Instead of weakening rapidly like ordinary sedimentary stone, some tuff blocks became denser over time. Researchers compared samples from the Wall of Romulus to stone used in later Roman structures such as the Servian Wall and portions of the Colosseum substructure. Surprisingly, some early blocks showed durability levels approaching those from much later imperial projects. This raises a disturbing possibility. The builders may have possessed generations of empirical geological knowledge long before formal Roman engineering manuals existed. Ancient workers may have tested quarry stone through observation over decades, identifying which material resisted water, heat, and erosion best. If true, Rome's earliest engineers were conducting primitive materials science centuries before the concept even existed. The positioning of the Wall of Romulus may be even more mysterious than the wall itself. Rather than forming a simple circular barrier around houses, many sections follow elevated ridges around the Palatine Hill with carefully calculated sightlines. From several preserved points, defenders could monitor multiple approach routes simultaneously. Military historians studying the layout notice similarities to later defensive theories involving overlapping visual control zones. Certain angles allowed observers to detect movement near river crossings and lower valleys long before enemies approached the core settlement. For a supposedly primitive hilltop community, the strategic planning appears unusually advanced. Comparisons with early Greek colonies from the same era show that many lack defensive optimization of this complexity. Rome's earliest fortification already demonstrates awareness of elevation advantage, surveillance geometry, and terrain funneling. Some archaeologists speculate the wall was not built all at once, but evolved through repeated military conflicts. Burn layers discovered beneath repair phases suggest attacks or raids occurred multiple times during the city's earliest centuries. Each reconstruction phase appears more refined than the previous one, almost as though Rome used the wall itself as a long-term engineering experiment. The Wall of Romulus was not merely military architecture, it was psychological architecture. According to Roman tradition, the city boundary, called the Pomerium, possessed sacred power. Crossing it unlawfully was considered a direct attack against the city's divine order. Legend claims Romulus killed his brother Remus after he mocked the defensive boundary by leaping over it. Whether true or not, the story reveals something important. The wall functioned as both a physical and symbolic technology of control. Anthropologists comparing Rome with other ancient civilizations noticed that early Roman identity became deeply tied to protected boundaries. The wall separated civilization from chaos, citizen from outsider, sacred land from hostile territory. Unlike many Bronze Age settlements where walls served mainly defensive purposes, Rome transformed fortifications into instruments of political unity and religious authority. The engineering of the structure, therefore, cannot be separated from the engineering of belief itself. Excavations reveal repeated destruction and rebuilding at Wall of Romulus. Burn layers, cracked stones, and replacement masonry suggest the wall endured multiple disasters over centuries. But each reconstruction introduced better engineering. Later sections used stronger stone alignment, improved drainage, and thicker support bases, showing that Roman builders were refining techniques through experience and failure. Some methods seen in the earliest layers later vanished, only to reappear centuries afterward in advanced Roman military architecture. This suggests parts of early Roman engineering knowledge may have been lost or forgotten over time. The Wall of Romulus may therefore preserve some of the oldest experimental engineering techniques in Roman history. Do you think the Wall of Romulus was built using knowledge far ahead of its time? Or are we still underestimating how advanced ancient civilizations really were? Share your thoughts in the comments below. Tipasa on Algeria's Mediterranean coast, about 70 kilometers west of Algiers, should not have become one of the Roman Empire's most successful maritime cities. Built on a shoreline exposed to waves, erosion, shifting sediments, and changing sea levels, the city flourished for centuries as a commercial hub connecting North Africa with the wider Mediterranean world. Today, its ruins reveal temples, basilicas, roads, water systems, cemeteries, and harbour structures. Yet the greatest mystery is not what survives. It is how ancient engineers created and maintained a functioning port on a coastline that should have constantly worked against them. The ancient city of Tipasa was originally established as a Phoenician trading post sometime before Roman control of the region. it expanded significantly after the Roman annexation of Mauritania in AD 40 and reached its peak between the 2nd and 4th centuries AD. Modern archaeological investigations began during the 19th century under French researchers, while extensive excavations throughout the 20th century uncovered large portions of the city. In 1982, Tipasa was designated a UNESCO World Heritage Site. Despite more than a century of research, many of its most important engineering secrets remain unsolved. The first and most fascinating mystery concerns the harbour itself. Ancient ports were extremely vulnerable to natural forces. Even modern engineers struggle to maintain navigable harbours without dredging, equipment, satellite monitoring, and hydrodynamic modelling. Coastal sediments transported by waves and currents can gradually fill channels and basins, rendering ports unusable. This process has affected countless ancient harbours across the Mediterranean. The harbour of Ephesus in modern Turkey, for example, was eventually stranded kilometres inland due to sediment accumulation from the Cayster River. Similar problems affected ports in Egypt, Greece, and Italy. Tipasa somehow avoided this fate for centuries. Archaeological evidence suggests that its harbour remained operational throughout much of the Roman period, despite being located on a coastline exposed to complex marine processes. Researchers studying Mediterranean coastal geomorphology have found that even minor changes in current patterns can dramatically alter sediment deposition rates. Yet the harbour's position appears remarkably effective. The obvious question is how ancient engineers selected the site. They possess no sonar systems, bathymetric surveys, aerial photography, or computer simulations. Nevertheless, they identified a location capable of supporting maritime trade for generations. Some scholars believe Roman engineers relied on centuries of accumulated observations from Phoenician sailors and local navigators. Others argue that systematic coastal surveying techniques may have existed that are poorly documented in surviving texts. The mystery deepens because no detailed engineering records from Tipasa have survived. We know the harbour worked, we know ships used it, we know trade flourished. What remains unknown is exactly how its designers predicted long-term coastal stability with such apparent success. The second mystery involves the city's relationship with water. Tipasa was constructed across uneven coastal terrain descending toward the Mediterranean. Such landscapes create serious engineering challenges. Heavy rainfall can generate destructive runoff, while poorly designed drainage systems can undermine foundations and accelerate erosion. Excavations have revealed an extensive network of channels, cisterns, reservoirs, and underground drains distributed throughout the city. Portions of these systems remain visible today. What astonishes researchers is the efficiency of the design. Roman hydraulic engineering is famous throughout the ancient world, yet many details of Tipasa's integrated water network remain unclear. Archaeologists have identified individual components, but reconstructing the complete hydraulic system remains difficult because many sections remain buried or destroyed. Similar challenges exist at sites such as Leptis Magna in Libya and Pompeii in Italy, where surviving infrastructure suggests a level of urban water management far more sophisticated than earlier historians imagined. At Tipasa, engineers successfully balanced freshwater storage, wastewater removal, flood prevention, and urban growth without modern pumps or reinforced concrete. Exactly how all these elements function together remains only partially understood. The third mystery concerns the remarkable durability of the city's construction. Northern Algeria lies within a tectonically active region influenced by the ongoing convergence of the African and Eurasian plates. Historical records document destructive earthquakes throughout the broader Mediterranean basin. Despite this geological reality, substantial portions of Tipasa survived for nearly 2,000 years. Walls, foundations, religious structures and civic buildings continue to stand despite centuries of natural and human disturbances. Modern structural engineers studying Roman architecture have repeatedly discovered techniques that distributed loads more effectively than expected. Certain walls at Tipasa display unusual thicknesses and foundation strategies that may have improved long-term stability. Whether these features were intentionally designed to resist seismic forces remains uncertain. Similar debates surround structures such as the Colosseum in Rome and Roman aqueducts in Spain and France. Ancient builders may not have understood plate tectonics, but they clearly possessed practical knowledge gained through generations of construction experience. The extent of that knowledge remains difficult to measure. Another mystery centers on the materials themselves. Roman concrete has become one of the most studied ancient technologies in the world. Scientific analyses conducted during the 21st century reveal that certain Roman marine concretes become stronger over time through chemical interactions with seawater. Researchers identified minerals such as aluminous tobermorite forming within ancient concrete, contributing to exceptional durability. Modern Portland cement often begins degrading after decades in marine environments. While some Roman structures have survived for nearly 2 millennia, Tipasa presents an intriguing case because its coastal structures endured constant exposure to salt, humidity, and marine conditions. Material analyses indicate the use of local aggregates and regionally available resources. However, researchers still debate whether builders at Tipasa employed modified construction recipes adapted specifically for North African environmental conditions. If they did, much of that technical knowledge disappeared long ago. Like the formula behind Roman marine concrete itself, the precise methods used at Tipasa remain only partially reconstructed through modern laboratory analysis. The city's urban planning introduces another layer of mystery. Viewed from above, the arrangement appears deliberate and highly organized. Roads connect residential districts, religious complexes, commercial zones, cemeteries, and harbor facilities in a coherent pattern that maximizes available terrain. Such planning required accurate surveying, measurement, and long-term vision. Roman surveyors possessed instruments such as the groma and chorobates, but surviving evidence rarely explains how they adapted these tools to challenging coastal landscapes. The precision achieved at Tipasa becomes even more impressive when compared with the limitations of ancient technology. No satellites guided construction. No digital elevation models existed. No geographic information systems processed topographic data. Yet engineers successfully integrated transportation, water management, commerce, and defense into a functioning urban environment. The planning resembles achievements seen at Timgad in Algeria and other major Roman cities, but Tipasa faced the additional complication of an unstable maritime setting. What do you think was the greatest achievement at Tipasa? The harbour engineering, the water management system, or the construction techniques that survived for centuries? Share your thoughts in the comments below. Chauvet Cave, located in the limestone cliffs of the Ardèche region in southern France, contains artwork so sophisticated that when scientists first revealed its age, many experts believed the dating had to be wrong. The paintings appeared too advanced, too realistic, and too technically accomplished for people who lived more than 36,000 years ago. Yet repeated radiocarbon tests confirmed the astonishing result. Long before the pyramids of Egypt, before Stonehenge, and even before agriculture, metallurgy, or written language, Ice Age artists ventured into the darkness of Chauvet and created images whose complexity continues to challenge modern understanding. The cave itself was rediscovered on December 18, 1994, when 3 speleologists, Jean-Marie Chauvet, Eliette Brunel, and Christian Hilaire, noticed a powerful draft emerging from a small opening in the rock. After crawling through a narrow passage, they entered chambers untouched for tens of thousands of years. What they found was one of the greatest archaeological discoveries of the 20th century. More than 1,000 images covered the walls, including over 400 animal depictions representing at least 14 species. Lions, rhinoceroses, cave bears, mammoths, bison, horses, and extinct predators appeared across the cave in extraordinary detail. Unlike many prehistoric sites dominated by herbivores, Chauvet featured dangerous carnivores in unprecedented numbers. It was immediately clear that this was not merely decoration. It represented a sophisticated visual culture whose origins remain mysterious. The first puzzle emerged from the artistic quality itself. For more than a century, archaeologists had generally assumed that prehistoric art evolved gradually from simple symbols towards realism. Chauvet shattered that model almost overnight. Some of its paintings display perspective, shading, anatomical accuracy, and motion effects that appear comparable to techniques developed thousands of years later. In the famous panel of horses, subtle variations in line thickness create depth and volume. In the gallery of lions, multiple overlapping heads generate the illusion of movement, resembling a sequence of animation frames. Similar principles would not formally appear in visual theory until modern times. The question is unavoidable. How did people living during the Orinocean period possess artistic capabilities that seem to leap far ahead of expected cultural development? The mystery deepens when examining where these paintings were created. Many are located hundreds of meters inside the cave, far beyond the reach of natural daylight. Reaching these chambers required navigating complex passages, uneven terrain, and complete darkness. Scientific analysis has revealed traces of torches and stone lamps fueled by animal fat. Yet producing artwork under such conditions would have required careful planning and environmental understanding. Smoke from torches can quickly make underground spaces uninhabitable. Nevertheless, Chauvet's artists repeatedly worked deep within the cave over extended periods. Some researchers suspect they possessed a practical knowledge of air circulation and cave ventilation that allowed them to choose locations where smoke dispersed naturally. Although impossible to prove directly, the evidence suggests a level of environmental awareness rarely associated with Upper Paleolithic societies. Even more surprising is the preparation of the cave walls themselves. Detailed examinations show that many surfaces were intentionally cleaned before painting. Artists scraped away mineral deposits and rough layers of limestone to create smoother backgrounds. In some areas, they selected wall contours that enhanced the shape of the intended image. Natural bulges became the shoulders of bison. Curved rock surfaces transformed into the flanks of horses. Cracks in the limestone were incorporated into animal outlines. Rather than treating the wall as a flat canvas, the artist used three-dimensional geology as part of the composition. This required not only technical skill but also advanced spatial visualization. They were effectively combining painting and sculpture into a single artistic process more than 30 millennia before classical civilizations emerged. Yet the greatest technological mystery of Chauvet may lie in something far less visible: the pigments. At first glance, the cave's black and red images seem straightforward. Black figures were primarily created using charcoal, while red images relied on iron-rich ochre. However, decades of scientific analysis have revealed that the process was far more complex than originally believed. The pigments have survived for over 30,000 years with remarkable clarity. In some areas, lines remain crisp enough to reveal individual strokes. The durability of these materials has become one of the most intriguing unsolved questions in prehistoric technology. Laboratory studies show that the charcoal used in many black paintings was not randomly selected. much of it appears to have come from specific types of pine wood. Experimental archaeology demonstrates that different woods produce charcoal with different textures, carbon structures, and drawing characteristics. Pine charcoal creates darker, more consistent lines than many alternatives. This suggests deliberate material selection rather than accidental availability. The artists may have understood, through generations of experimentation, which woods produced the best visual results. If true, this represents a form of practical materials science thousands of years before the concept itself existed. The red pigments raise even more questions. Ochre is found throughout prehistoric sites across the world, yet Chauvet's red images exhibit unusual consistency and longevity. Microscopic analysis indicates that the pigment particles were often processed before application. Some researchers believe the minerals were crushed to carefully controlled grain sizes. Others suggest the artists may have separated impurities from the raw material to improve color quality. The exact methods remain unknown because the tools and preparation areas have largely disappeared. What survives is only the finished result. Like modern engineers examining an ancient machine without its blueprint, researchers can observe the outcome but not the complete manufacturing process. The possibility of organic binders introduces another layer of mystery. Certain pigments appear to adhere to the rock more effectively than simple dry powder would allow. Some scientists have proposed that animal fat, marrow, blood, plant resins or other organic substances may have been mixed with mineral pigments. Such additives could improve adhesion, alter texture, and increase durability. Yet after tens of thousands of years, direct evidence is difficult to detect. If these mixtures were used, Chauvet's artists may have possessed sophisticated empirical knowledge of chemical interactions, without any formal understanding of chemistry itself. Comparisons with other prehistoric sites make the puzzle even greater. The famous cave paintings of Lascaux Cave date to roughly 17,000 years ago, while the paintings of Altamira Cave are approximately 14,000 to 20,000 years old. Both are celebrated masterpieces of Paleolithic art. Yet Chauvet predates them by nearly 15,000 to 20,000 years while already displaying comparable levels of sophistication. If artistic development followed a simple linear progression, Chauvet should appear more primitive. Instead, it appears astonishingly mature from the very beginning. This reversal of expectations remains one of the most important debates in Paleolithic archaeology. The cave also contains evidence suggesting an unexpected understanding of visual perception. Several images use shading techniques achieved by rubbing charcoal against the wall and blending it with fingers. This creates gradients that generate a sense of volume and depth. Such methods resemble artistic practices employed by Renaissance masters tens of thousands of years later. Some animal groups are arranged to exploit the flickering light of torches. As flames moved, overlapping outlines may have appeared to animate. Whether intentional or accidental remains uncertain, but the effect is striking. It raises the possibility that Chauvet's artists understood aspects of motion perception in ways that modern observers are only beginning to appreciate. Acoustic studies suggest that many major artworks in Chauvet Cave are located in chambers with unusual sound properties, such as strong echoes and resonance. Similar patterns appear in other decorated caves across Europe. Researchers believe sound may have influenced the choice of sacred spaces, showing that Chauvet's artists created immersive environments combining sound, light, space, and imagery. This reflects a high level of cultural and cognitive sophistication among Ice Age people. How do you think people 36,000 years ago mastered such sophisticated artistic and technical skills? Let us know your theory in the comments below. Hemudu is one of the oldest and most puzzling archaeological sites ever discovered in China. Located in Yuyao, Zhejiang province, near the southern edge of Hangzhou Bay, the site preserves evidence of a sophisticated society that flourished between approximately 5,000 and 3,300 BC. More than 7,000 years ago, while much of the world was still transitioning from hunting and gathering to settled farming, the people of Hemudu were constructing large wooden buildings, cultivating rice on a significant scale, producing lacquerware, and developing technologies that continue to challenge archaeologists today. The discovery itself was accidental. In 1973, workers involved in a water conservancy project unearthed unusual artifacts buried beneath thick layers of waterlogged soil. Archaeologists soon arrived and launched excavations that revealed one of the most important Neolithic settlements in East Asia. Over multiple excavation seasons, researchers uncovered more than 6,000 square meters of cultural deposits, thousands of artifacts, extensive wooden architecture, animal remains, and one of the largest collections of early rice remains ever found in China. What emerged was not merely a prehistoric village, but a technological puzzle that still raises questions more than 5 decades after its discovery. The first mystery concerns the astonishing wooden engineering of Hemudu. Wood is one of the least likely materials to survive for thousands of years, yet archaeologists recovered hundreds of wooden structural components, including pillars, beams, planks, tools, and architectural elements. Some of these pieces reveal the use of mortise and tenon joints, a sophisticated woodworking technique in which precisely carved projections fit into matching cavities without the need for nails or metal fasteners. The same principle would later become a defining feature of traditional Chinese architecture, including structures built thousands of years later. The mystery is not that the joints existed, but that they appeared so early. During the Hemudu period, metal tools had not yet become available. Most cutting and shaping was performed using polished stone axes, adzes, and bone implements. Modern experiments have shown that creating accurate mortise and tenon joints using stone tools is possible, but extraordinarily labor-intensive. Some joints discovered at Hemudu display levels of precision that seem surprising for a society operating entirely without metallurgy. The question remains, how did these craftsmen achieve such accuracy, and how much practical engineering knowledge has been lost? The second mystery involves the construction of large stilt house settlements in an environment that should have been difficult to inhabit. Geological studies indicate that the Hemudu region was characterized by wetlands, tidal influences, flooding, and unstable soils. Yet the inhabitants developed extensive raised wooden structures supported by deep piles driven into the ground. Excavated post holes suggest substantial buildings elevated above the surrounding terrain. This design protected residents from seasonal flooding and damp conditions. Modern engineers rely on soil analysis, geotechnical surveys, and sophisticated calculations when building on unstable ground. Hemudu builders possessed none of these technologies, yet their structures endured long enough to leave a significant archaeological record. Researchers continue to debate how these early communities assessed ground stability and selected construction sites with such effectiveness. The third mystery centers on rice agriculture. Hemudu yielded enormous quantities of rice remains, including grains, husks, leaves, and stalk fragments. Some estimates suggest that several tons of rice-related material were preserved at the site. Radiocarbon dating places many of these remains at more than 6,500 years old. Rice cultivation is often underestimated as a technological achievement. Unlike simple gathering, successful rice farming requires water management, seasonal planning, land preparation, storage systems, and knowledge accumulated across generations. Evidence from Hemudu suggests that rice was not merely collected, but systematically cultivated. The scale of production indicates an organized agricultural economy capable of supporting a substantial population. The mystery lies in how quickly this expertise developed. Compared with many contemporary Neolithic communities elsewhere in the world, Hemudu appears remarkably advanced in agricultural adaptation. Some scholars argue that the lower Yangtze region may have been one of the world's independent centers of rice domestication, but the exact process remains poorly understood. The fourth mystery concerns environmental adaptation and survival. Paleo-environmental studies indicate that sea levels and climate conditions in eastern China changed significantly throughout the Holocene period. The inhabitants of Hemudu lived in a dynamic landscape shaped by rivers, marshes, storms, and coastal influences. Despite these challenges, they maintained a stable settlement for centuries. Animal remains reveal a mixed economy involving hunting, fishing, gathering, and farming. The community exploited deer, wild boar, fish, birds, and aquatic resources while simultaneously cultivating crops. Such flexibility suggests a sophisticated understanding of local ecosystems. Yet archaeologists still struggle to explain how these populations balanced environmental risks and resource management over such long periods without written records or centralized administrative systems. The fifth mystery, and perhaps the most extraordinary of all, is the appearance of early lacquer technology. Among the discoveries at Hemudu were wooden objects coated with red lacquer. Scientific analysis confirmed that the coating originated from the sap of the lacquer tree, Toxicodendron vernicifluum. This finding stunned researchers because lacquer production is one of the most technically demanding crafts of the ancient world. Unlike simple paint, lacquer requires collecting sap from specific trees, filtering impurities, processing the material, and applying it in carefully controlled layers. The curing process depends on precise humidity and temperature conditions. If conditions are too dry, the lacquer hardens improperly. If conditions are too wet, the surface can be damaged. Even traditional lacquer workshops operating thousands of years later required specialized knowledge and controlled environments. The Hemudu lacquer artifacts date to roughly 5000 BC, making them among the earliest known lacquered objects ever discovered anywhere on Earth. This pushes the history of lacquer technology back more than 7 millennia. To appreciate the significance of this achievement, consider a comparison. Ancient Egypt was still more than 2,000 years away from the construction of the Great Pyramid. Stonehenge would not begin to take shape for another 2,000 years, yet the people of Hemudu were already experimenting with a sophisticated organic coating technology that would remain important throughout Chinese history. The mystery is not simply how they discovered lacquer, but how they mastered it. Producing useful lacquer requires repeated experimentation and long-term observation. Researchers still cannot determine how many generations of trial and error preceded the lacquerware found at Hemudu, nor can they fully explain why such advanced material knowledge appeared so early in prehistory. Some archaeologists describe lacquer as one of the first examples of humanity deliberately engineering natural chemical substances to create durable manufactured materials. The sixth mystery involves the remarkable preservation of organic materials. Most Neolithic sites yield stone tools, pottery fragments, and bones because organic materials usually decay rapidly. Hemudu is different. Waterlogged conditions preserved wood, plant fibers, woven objects, and food remains that would normally disappear. This preservation provides an unusually detailed glimpse into daily life. Yet it also creates scientific challenges. Researchers continue investigating the exact environmental conditions that allowed so many fragile materials to survive for over 7,000 years. Understanding these processes has become important not only for archaeology but also for conservation science. The seventh and perhaps greatest mystery concerns disappearance. The Hemadu culture flourished for centuries and developed technologies that appear surprisingly sophisticated for its age. Then, over time, it transformed and eventually vanished from the archaeological record as a distinct cultural entity. Climate change, flooding, sea level fluctuations, migration, and cultural integration have all been proposed as explanations. None fully account for the transition. What happened to the craftsmen who mastered woodworking? What became of the communities that pioneered lacquer production? Where did their accumulated knowledge go? Risen ancient city, known in antiquity as Reason, lies on the northern shore of the Bay of Kotor in present-day Montenegro. The ancient settlement occupies one of the most protected natural harbours in the Adriatic Sea, surrounded by steep limestone mountains and deep coastal waters. Archaeological investigations began in the 19th century and expanded significantly during the 20th and 21st centuries, revealing evidence of an important Illyrian and later Roman urban centre. Excavations uncovered defensive walls, residential districts, imported goods, coins, and some of the finest Roman mosaics found in the Balkans. Yet despite decades of research, many of the technologies and engineering systems that allowed Rison to become a powerful maritime city remain poorly understood. The greatest mystery of Rison begins with geography. The Bay of Kotor stretches nearly 30 kilometers inland and forms one of the most unusual natural harbours in Europe. Surrounded by mountains rising more than 1,500 meters above sea level, the bay resembles a fjord despite being formed through different geological processes. Rison occupied one of the safest positions within this protected water system. Ancient sailors faced constant threats from storms, piracy, and unpredictable currents. Most ancient ports relied heavily on artificial breakwaters and harbour engineering, yet Rison benefited from natural protection that rivaled some of the greatest naval bases of antiquity. The mystery is not that the harbour existed. The mystery is why the Illyrians selected this exact location centuries before modern hydrographic surveys could measure currents, wave energy, or navigational safety. Modern naval planners analyze countless variables before establishing strategic ports, yet Rison appears to have achieved similar advantages more than 2,300 years ago. Archaeologists continue debating whether this was the result of generations of accumulated maritime knowledge or whether Illyrian navigators possessed a much deeper understanding of coastal geography than historical sources suggest. The harbour's strategic value became so obvious that later Roman authorities maintained and expanded the settlement rather than abandoning it. This continuity suggests that Rison occupied one of the most valuable maritime positions anywhere along the eastern Adriatic coast. The Bay of Kotor region receives exceptionally high rainfall, and some nearby mountain areas experience annual precipitation exceeding 4,500 millimeters, among the highest recorded in Europe. For an ancient city, such conditions created enormous challenges. Heavy rainfall increases erosion, destabilizes foundations, damages roads, and complicates urban planning. At the same time, the surrounding karst landscape causes water to disappear underground through limestone formations, making long-term water management extremely difficult. Despite these challenges, Rison survived for centuries, raising one of the most fascinating engineering questions associated with the site. How did its inhabitants manage water? Excavations have revealed portions of drainage systems and urban infrastructure, but archaeologists still lack a complete understanding of how the city controlled runoff, protected buildings from flooding, and maintained reliable freshwater supplies. The mystery becomes even more significant when compared with other ancient civilizations. The Romans built aqueducts stretching over 80 kilometers, The Nabateans engineered sophisticated water storage systems at Petra, and the Minoans constructed advanced drainage networks on Crete nearly 4,000 years ago. Yet Rhizon operated successfully within one of the most hydrologically complex environments in the Adriatic. Many researchers suspect that substantial portions of its hydraulic infrastructure remain buried beneath modern construction or unexplored archaeological layers. For centuries, classical authors often portrayed the Illyrians as tribal peoples living beyond the boundaries of major Mediterranean civilizations. Archaeology has gradually destroyed that stereotype. Excavations at Rhizon reveal imported ceramics from Greece, luxury goods from across the Mediterranean, locally minted coinage, monumental architecture, and evidence of extensive commercial activity. The quantity of imported artifacts indicates participation in long-distance trade networks spanning hundreds and possibly thousands of kilometers. This creates another mystery. Where did all this wealth originate? Trade alone may not fully explain the city's prosperity. Some scholars believe Rhizon controlled critical maritime routes connecting the Adriatic with inland Balkan markets, while others suggest it served as a redistribution centre, where goods arriving from the Mediterranean were exchanged for resources from the interior. Yet the precise economic mechanisms remain uncertain. Unlike Rome, Athens, or Carthage, Rhizon left few written records explaining how its economy functioned. As a result, archaeologists can see evidence of wealth but cannot fully reconstruct the system that generated it. One of the most important discoveries at the site involves coin production. Rhizon minted its own currency during periods of Illyrian rule, a remarkable achievement for a regional power. Ancient coinage represented far more than money. Coins required access to metals, skilled craftsmen, standardized production techniques, political authority, and organized economic systems. The existence of Rhizon's coinage suggests a level of administrative sophistication far beyond what was once attributed to Illyrian societies. Yet mysteries remain. How large was the minting operation? Where did the metal originate? How extensive was the circulation network? Coins linked to Rhizon have been found across parts of the Balkans, indicating influence extending well beyond the city itself. Some researchers compare this phenomenon to other ancient trading powers, whose political influence exceeded their physical size. The evidence suggests Rhizon played a much larger regional role than historians once imagined. Ancient ports rarely functioned through geography alone. Successful maritime centers required warehouses, docks, ship repair facilities, storage yards, administrative buildings, and systems for loading and unloading cargo. Yet, surprisingly little of Rhizon's harbour infrastructure has been identified with certainty. This absence creates one of the site's most intriguing archaeological puzzles. A city engaged in extensive maritime trade should have left behind substantial evidence of commercial facilities, but where are they? Some researchers believe portions of the ancient harbour now lie beneath accumulated sediments. Others suspect rising sea levels, tectonic activity, and centuries of shoreline modification may have altered the original coastal landscape beyond recognition. Modern underwater archaeology has transformed understanding of ancient ports across the Mediterranean, and sites once thought lost have reappeared beneath meters of sediment and seawater. Rhizon may conceal similar discoveries waiting offshore. Perhaps the most overlooked mystery involves knowledge itself. Rhizon's builders selected a defensible location, established successful maritime connections, developed urban infrastructure, managed complex environmental conditions, and participated in international trade. These achievements required expertise in navigation, engineering, logistics, and economics. Yet almost none of the technical manuals, instructions, calculations, or records behind those achievements survive. Do you think the greatest mystery of Rhizon is its lost harbour technology, its unexplained wealth, or the disappearance of Illyrian knowledge? Share your thoughts in the comments below. Perched above the Alazani Valley in eastern Georgia, Gremi was once the thriving capital of the Kingdom of Kakheti and a key crossroads linking Persia, Anatolia, the Black Sea, and the trade routes of the Silk Road. Although only fragments of the city remain today, its ruins reveal a remarkable story of innovation and ambition. Beneath the surviving towers, churches, and defensive walls lies evidence of sophisticated engineering that historians are still working to fully understand. Among all its mysteries, one stands above the rest: a ceramic water supply system that may have been one of the most advanced hydraulic networks in the region during the 16th century. The ruins of Gremi stand in Georgia's Kakheti region, approximately 175 kilometers east of Tbilisi. The city served as the capital of the Kingdom of Kakheti during the 16th century under King Levan. Although travelers had described the ruins for centuries, systematic archaeological investigations began during the 20th century and intensified after the 1930s. Excavations uncovered the remains of palaces, churches, baths, workshops, fortifications, roads, water systems, and residential districts. Archaeologists soon realized that the surviving fortress represented only a small part of a much larger urban center that once covered roughly 40 to 50 hectares. The first mystery concerns the ceramic water supply system. Water management has always been one of the defining characteristics of advanced civilizations. The Romans built aqueducts stretching for tens of kilometers. The Persians developed underground qanat systems capable of transporting groundwater across deserts. Yet Gremi presents a different puzzle. Archaeologists discovered networks of ceramic pipes buried beneath the city, connecting water sources with baths, fountains, administrative buildings, and residential areas. At first glance, ceramic pipes may not seem extraordinary. However, the engineering challenges become apparent when the terrain is examined. Gremi was built on elevated ground overlooking the Alazani Valley. Maintaining a consistent water flow across uneven slopes required careful calculations of gradient and pressure. Even a slight miscalculation could cause stagnation, pipe failure, or insufficient supply. The ceramic sections were manufactured with standardized dimensions and joined together with surprising precision. Modern surveys suggest that some pipe segments maintained gradients measured in only a few centimeters over significant distances. Such precision is comparable in principle to techniques employed by Roman hydraulic engineers centuries earlier. The greatest mystery is how the engineers surveyed the landscape. No written technical manuals survive. There is no evidence that the builders possessed advanced measuring instruments comparable to modern levels or transit equipment. Yet the water network functioned efficiently enough to support a growing capital city. Researchers continue debating whether the system evolved from local Caucasian traditions or whether Persian influence played a significant role. During the 16th century, the Caucasus stood at the crossroads of competing empires. Trade routes connected Gremi to Persian cities renowned for hydraulic engineering. It is possible that foreign craftsmen introduced specialized knowledge. Another possibility is even more fascinating. Local engineers independently developed solutions adapted to the mountainous terrain of eastern Georgia. Comparisons with contemporary settlements highlight the achievement. Many fortified cities of the region relied primarily on wells and natural springs. Gremi appears to have integrated a planned distribution network, transforming water into an organized urban resource. This suggests a level of technical administration far beyond what many historians once assumed for the kingdom. The second mystery involves the fortress's hidden tunnel system. Historical accounts and archaeological evidence indicate the existence of a secret passage connecting the fortress to the nearby Intsoba River. Such passages were not uncommon in medieval fortifications, but constructing one beneath steep terrain presented enormous challenges. Excavations reveal that sections of the tunnel were cut through difficult geological formations while maintaining structural stability. Engineers had to prevent collapses, manage drainage, and conceal the entrance from potential attackers. Even today, not all portions of the passage have been fully investigated. The existence of the tunnel raises important questions. How extensive was the underground network? Was it intended solely for water access during sieges, or did it also function as an escape route and supply corridor? Some researchers believe additional unexplored sections may still remain buried beneath centuries of sediment. The third mystery concerns urban planning. Satellite surveys and archaeological excavations reveal that Gremy was not merely a fortress. It was a carefully organized city. Residential quarters, markets, workshops, religious buildings, and administrative centers were arranged according to a broader plan. Creating such a city required more than construction skills. It required surveying expertise, resource management, and logistical coordination. Tens of thousands of tons of stone, timber, bricks, and ceramic materials had to be transported and assembled. This challenge becomes even more impressive when compared with other regional capitals. Unlike cities built on broad plains, Gremy occupied a strategically elevated position. Engineers had to adapt streets, drainage systems, and foundations to uneven terrain while maintaining defensive effectiveness. Archaeological evidence indicates that workshops produced ceramics, metal goods, and construction materials locally. This suggests a highly organized economy capable of supporting large-scale building programs. Yet records explaining how labor was organized remain scarce. The fourth mystery centers on architectural technology. The surviving Archangel's Church demonstrates a blend of Georgian and Persian influences rarely seen elsewhere. Stone masonry, decorative brickwork, and glazed elements appear together in a unique architectural synthesis. The builders achieved remarkable structural stability despite the region's seismic activity. Earthquakes have affected the Caucasus throughout history, yet major portions of the complex survived for centuries. Researchers continue studying construction techniques used in the walls and foundations to understand how they resisted environmental stresses. Particularly intriguing is the combination of local stone and imported stylistic features. This mixture suggests extensive cultural exchange. However, historians still debate whether foreign specialists worked directly on the site or whether local craftsmen adapted imported ideas using indigenous methods. The fifth mystery involves defense engineering. The fortress occupies one of the most strategically advantageous locations in eastern Georgia. From its elevated position, defenders could observe movement across large sections of the Alazani Valley. Visibility extended across major transportation corridors connected to regional trade routes. The walls and towers were designed not only to resist attack, but also to maximize surveillance. Defensive architecture exploited natural terrain, reducing the need for massive artificial barriers. Similar principles appear in famous fortresses such as Krak des Chevaliers in Syria and the hilltop castles of Anatolia. Yet one question remains unresolved. How many soldiers were required to defend a city of this scale? Estimates vary significantly because surviving military records are incomplete. The relationship between the fortress itself and the broader urban population remains poorly understood. The sixth mystery is the city's sudden destruction. In 1615, Shah Abbas III of Persia launched a devastating campaign against Kakheti. Historical sources describe widespread destruction throughout the region. Gremy, despite its formidable defenses and strategic importance, never fully recovered. The speed of the collapse surprises historians. A city possessing advanced infrastructure, strong fortifications, and regional economic importance should theoretically have been capable of prolonged resistance. Some scholars argue that gunpowder warfare fundamentally altered the balance. Defensive systems optimized for earlier forms of siege warfare became increasingly vulnerable to artillery. Others point to demographic disruption, economic devastation, and political instability. The precise sequence of events remains uncertain because surviving accounts are incomplete and often contradictory. What do you think was Gremmy's greatest mystery? The ceramic water system, the hidden tunnel, or the lost engineering knowledge behind the entire city? Share your thoughts in the comments below. Rabat Malik stands among the great engineering enigmas of the Silk Road. Located on the arid plains of present-day Uzbekistan between Bukhara and Samarkand, its ruins seem modest at first glance. Yet nearly 1,000 years ago, this complex ranked among the most sophisticated structures in Central Asia. Archaeologists have uncovered massive fortifications, monumental gateways, advanced hydraulic systems, and architectural features that continue to puzzle researchers. Despite decades of excavation, scholars still debate its true purpose, the construction techniques behind it, and how its builders created a self-sustaining complex in one of the harshest environments along the Silk Road. The story of Rabat Malik began not with ancient texts, but with ruins visible to travelers crossing Central Asia. Russian explorers and scholars documented the surviving gateway during the 19th century, while major archaeological investigations throughout the 20th century gradually revealed the buried remains of a much larger complex. Excavations showed that the site was not merely a roadside caravanserai. Beneath the sands lay evidence of a fortified royal residence, extensive courtyards, service buildings, water infrastructure, and defensive walls covering thousands of square meters. Every new discovery raised more questions than answers. The first mystery concerns the true function of Rabat Malik. Historical sources generally describe it as a caravanserai, a stopping point for merchants traveling between the great cities of Transoxiana. Yet the architecture suggests something far more complex. The complex occupied an area estimated at over 8,000 square meters. Its monumental entrance featured elaborate geometric decoration, intricate brickwork, and structural sophistication rarely found in ordinary commercial facilities. Archaeologists discovered evidence of multiple courtyards, residential sections, religious spaces, and administrative areas. Comparisons with other Silk Road caravanserais reveal significant differences. Many caravanserais were designed primarily for protection and accommodation. Rabat Malik, however, displays characteristics associated with elite architecture. Some researchers believe it may have served as a royal palace for Karakhanid rulers before later being converted into a caravanserai. Others argue that it functioned as both a palace and a strategic trade station simultaneously. This uncertainty creates a fascinating paradox. If Rabat Malik was only a caravanserai, why was it built on such an extraordinary scale? If it was a palace, why was it located in the middle of a semi-arid steppe far from major urban centres? Nearly a millennium later, scholars still disagree. The second mystery, and perhaps the most remarkable technological puzzle, is the water supply system hidden beneath the dry steppe. Today, the landscape surrounding Rabat Malik appears unforgiving. Annual precipitation in much of the region is relatively low, and summer temperatures frequently exceed 40 degrees Celsius. Sustaining hundreds of travelers, animals, servants, guards, and residents would have required a reliable water source throughout the year. Yet archaeological evidence indicates that Rabat Malik possessed exactly such a system. Researchers discovered ceramic pipelines, underground channels, storage facilities, and connections to one of Central Asia's most impressive hydraulic structures, the Sardoba Malik Reservoir. Located near the complex, the Sardoba is a massive domed water storage system approximately 13 meters high and more than 15 meters in diameter. The structure was designed to collect, preserve, and protect water from evaporation under extreme climatic conditions. What makes this system extraordinary is not simply its size, but the engineering knowledge required to make it function. Transporting water across long distances without modern pumps requires precise control of gradient. Even a slight error in elevation can prevent water flow entirely or create destructive pressure within channels. Modern engineers use laser surveying equipment, GPS systems, and digital terrain models to calculate such gradients. The builders of Rabat Malik relied on none of these technologies. How did they determine elevation differences across kilometers of open terrain? How did they maintain consistent flow rates? How did they prevent contamination and sediment buildup? These questions remain only partially answered. The challenge becomes even more impressive when compared to other ancient hydraulic systems. Roman aqueducts relied on carefully calculated gradients, averaging only a few centimeters per 100 meters. Persian qanats transported groundwater across deserts through underground tunnels extending for dozens of kilometers. The engineers of Rabat Malik appear to have applied similar principles in a Silk Road environment, where water management meant the difference between survival and abandonment. Some archaeologists argue that the hydraulic network represents inherited engineering traditions stretching back centuries through Persian, Sogdian, and Islamic civilizations. Others suggest local innovations adapted specifically for Central Asian conditions. Regardless of origin, the system demonstrates a level of environmental engineering that remains astonishing today. The third mystery involves the fortress-like design of the complex. Excavations revealed defensive walls, towers, controlled entry points, and a layout emphasizing security. The surviving gateway alone suggests a structure intended to project authority and withstand attack. Historical reconstructions indicate walls reaching considerable heights and enclosing large internal spaces. This raises an obvious question. Why would a roadside accommodation facility require military-grade defences? The answer may lie in the strategic importance of the Silk Road. During the 11th and 12th centuries, trade routes carried silk, spices, precious metals, ceramics, scientific knowledge, and diplomatic missions across Eurasia. Controlling these routes meant controlling wealth. Rabat Malik occupied a critical position between two of Central Asia's greatest cities, Bukhara and Samarkand. Any power seeking to monitor commerce, collect taxes, protect travellers, or project political influence would have benefited from maintaining a strong presence at this location. Yet the scale of fortification still appears excessive. Some researchers believe the structure served as a strategic royal outpost capable of housing military personnel alongside travellers. Others suggest that its defensive architecture reflected broader political instability during the Karakhanid period. The fourth mystery centers on construction technology. The surviving entrance of Rabat Malik is considered one of the masterpieces of Karakhanid architecture. The gateway incorporates complex geometric patterns, decorative brickwork, structural arches, and carefully engineered load distribution systems. Unlike simple masonry construction, monumental gateways must transfer enormous forces around openings while preventing collapse. Every brick contributes both decorative and structural functions. Modern structural analysis shows that such systems require sophisticated understanding of compression forces, material behavior, and geometric stability. What makes Rabat Malik particularly intriguing is the precision achieved using relatively simple materials. Builders relied primarily on fired bricks, clay mortars, and gypsum-based binding materials. Yet portions of the structure survived earthquakes, climate extremes, and centuries of neglect. Comparisons with contemporary Islamic architecture reveal similar innovations in cities such as Bukhara, Merv, and Samarkand. However, Rabat Malik remains unique because it combines monumental ceremonial architecture with practical frontier engineering. The fifth mystery concerns logistics. Constructing a complex of this scale required enormous resources. Thousands of tons of bricks had to be manufactured, transported, and assembled. Water systems required excavation and maintenance. Decorative elements demanded skilled artisans. Food and supplies had to support large workforces throughout construction. Modern estimates suggest that projects of comparable scale would require hundreds of labourers working for years. Organising such efforts demands administration, planning, surveying, and resource management. Yet almost nothing is known about the engineers who directed these operations. No construction manuals survive. No technical drawings have been discovered. No detailed descriptions explain how the project was organised. The builders left behind the results of their expertise, but almost none of the knowledge itself. Perhaps this is the greatest mystery of all.